Hey everyone, hope everyone's doing well. Sorry we started a little late, but yeah, we're putting the kids down, so just didn't go as planned. But yeah, hopefully they stay asleep. And yeah, let's get started. So I'll just say hi to the chat. Mark, Gregory, Shifty Eye Shady. Close this. And anybody else watching, thanks for being here. So I guess the title of the video, I guess the difference between optical and physical. So I guess before I get into optics and why optics shouldn't be trusted alone when we're dealing with motion of matter, I'll get into how accelerometers work and what are accelerometers and how they work. So I guess I'll get into that first. I'll go over a video here, I guess 6 or 7 different types of accelerometers, I think 6. And we'll be going over how the principles are basically the same, regardless of what accelerometer you use. So let's get started with that. So again, this is how an accelerometer works, 6 types of accelerometers. Oh, I'm not screen sharing, give me 1 sec. Share screen, let's go share screen. Okay, now we can get started here. Let's hide this. Okay, so we'll get started with this first video here.
The accelerometer is a type of sensor that, as its name suggests, is capable of detecting the acceleration of an object, or, in other words, detecting changes in its rate of displacement over a period of time. This type of sensor is used in hundreds of applications, including seismic sensors, mechanical systems analysis, and airbag activation during a crash, just to name a few. In fact, if you are watching this video from a phone, then you have an accelerometer in your hands at this very moment. Because of this versatility and the number of contexts in which the use of one of these sensors can be useful, in this video we will analyze how an accelerometer works and its different variants. We will start by analyzing how a
So right from the start, an accelerometer is a device that detects acceleration. So if you attach an accelerometer to an object and that object accelerates, then the accelerometer is going to detect that acceleration. So again, an accelerometer is simply a device that detects acceleration.
Mechanical accelerometer works in detail, as this will give us the theoretical basis to understand.
So a mechanical accelerometer will be like a simple accelerometer, like a water bottle with air and water, for example. That will be considered a mechanical accelerometer, but yeah.
How most of the other variants work. They are mainly composed of 3 elements: a base frame, a spring or some other elastic element, and finally, a mass. If we leave this system at rest, the distance between the mass and the base frame will remain stable. However, if we lift the entire system, the mass will move at a different speed than the base frame, and the distance between these 2 elements will increase and then stabilize again. In this simple action, multiple elements come into play, and they will allow us to know the acceleration of the system. The first of them we will take from Newton's first law, and is the use of an inertial reference frame, that is, a reference frame in which it is fulfilled that when the forces applied on an object are equal to 0, its acceleration will also be 0. In this case, our inertial reference system is the room in which we are performing the experiments, because, from our point of view, it is static. Within this system, when we lift our accelerometer we will be applying a force on the base frame, which will be transmitted to the spring and then to the mass, which causes everything to move, and it is a bit confusing to understand what is happening. To simplify,
again, what you can see when you apply an upwards force to this reference frame here with the spring, you can see that the spring elongates as if the weight of this is increasing and stretching the spring. But we know that the weight of this is not increasing on its own. It's only an effect of the system's upwards motion. And that's what gives you the stretch of the spring. The inertia of this mass wanting to remain motionless is what stretches the spring. But you need the motion of the reference frame in the upwards trajectory to begin with. So something to note.
To simplify this problem, we will fix our inertial reference frame on the base frame, ignoring what is happening on the outside. This time, when we analyze the behavior of the accelerometer, all we will see is that the mass goes up and down, which means there is a force being applied on it. More specifically, a fictitious force known as inertia force. Now,
Again, the downwards force or the inertial force, they even call it a fictitious force because, again, the resistance of matter, the weight of matter, it's not a real force on its own, in other words. So it's a fictitious force, in other words, or a pseudo force, in other words. So
now that we know that there is a force on the mass, the next step is to know the magnitude of that force, and for this we will rely on Hooke's law of elasticity, which relates the compression or elongation of a spring with the force that is being applied to it. More specifically, it tells us that the applied force is directly proportional to the variation of its length multiplied by an elastic constant, the latter being a characteristic of the spring used, and, therefore, a previously known constant. Understanding this, if we measure the length of the spring when it was at rest and calculate its difference with the length of the spring when the accelerometer moved, we will have all the necessary information to calculate the inertia force using Hooke's law. Now we are left with the last step, how to use the value of the inertia force to calculate the acceleration of the system. We will do this using Newton's second law, which tells us that the force applied on an object is equal to its mass multiplied by the acceleration generated as a result of that force. Although,
again, this simply means force equals ma is mass times acceleration, which just simply means an object that's in motion or matter that's in motion. So again, force is simply something that's moving.
as in this case we are interested in knowing the acceleration, we can rearrange the formula by saying that the acceleration of an object is equal to the force applied to it divided by its mass. This way, we get to know the acceleration without knowing its velocity of motion. We still have a small design problem though. Since the acceleration occurs over a short period of time, eventually the spring will cause the mass to return to its initial state, so it would be difficult to store this data manually for later calculations. An easy way to transfer this information is to make this same mass move some element capable of leaving a mark on a piece of paper, as well as to continuously move this paper so as not to overwrite the information generated. You probably already noticed, but what we have just built is basically a seismograph, one of the first types of accelerometers that were developed. In fact, to this day it's common to refer to the mass of the different types of accelerometers as seismic mass. This type of accelerometer, as well as several of the ones we will see later, are only capable of detecting accelerations on a single axis, because, if we decided to move it sideways, then the spring would bend to the side and we could no longer use Hooke's law to calculate the inertial force. Fortunately, we can use the same principle to measure accelerations in different axes by simply changing some elements or even just rotating the accelerometer. Mechanical accelerometers make it possible to obtain information without the use of complex circuits, since they only need a material such as paper to store it. However, this is also one of their limitations, since the reduction of the system would also mean the reduction of the written information and its accuracy. It is because of this, that currently most of the accelerometers used work by other methods that can be miniaturized and are able to deliver the information digitally, which are better known as MEMS or microelectromechanical systems. The first of the accelerometers in this category that we will discuss is known as a capacitive accelerometer. Capacitive accelerometers work in a similar way to mechanical accelerometers, the major difference being the way in which mass motion is converted into information. In this case, two plates of conductive material are used, a static one positioned in the system as a reference point and a dynamic one that moves along with the mass when it is affected by some acceleration. If we focus only on the metallic plates,
Again, in this accelerometer, although it's made up of different parts and not, the principles of displacement that detect the acceleration are the same. So again, this accelerometers depend on the displacement of matter within them to be able to register the force. Not only that, the direction of the force as well. Again, they all require moving parts, but these parts are not moving themselves. Again, they're simply displacing relative to the direction of the acceleration that's being applied.
we will realize that they form a capacitor, which, If we remember a little, are components capable of storing electrical charges which are mainly composed of three elements: a conductor, a dielectric or electrical insulator, and a conductor, being the dielectric simply the air in this case, because, this way, both plates are kept electrically separated while being able to move freely at the same time. Moreover, the capacitance, that is, the unit of measurement that indicates the capacity of a capacitor to store energy, can be calculated in simple cases as the dielectric constant of the material separating the conductors multiplied by the area of the conducting plates and divided by the distance between the two plates. In this formula, since we already know that the dielectric material is the air, we can look up its dielectric constant in a reference table, and furthermore, since someone must have built the accelerometer in the first place, the area of the conducting plates will also be known. Thus, the capacitance between the two plates will vary only as a function of the distance between them. In other words, we will have a way to translate the capacitance of the accelerometer into the mass displacement distance, the distance into a force, and the force into an acceleration. It may seem a bit convoluted, but we don't actually need to do these calculations every time we want to know the acceleration. Similar to the seismograph, where really all we were interested in was the final mark, here, all we are interested in is the voltage generated, which we can then check against a reference table that tells us what acceleration it corresponds to. If we start in a state of rest with a stable amount of electrical charges accumulated on the capacitor plates, and due to an acceleration these begin to gather, the capacitance will increase. When this happens, a greater amount of charge carriers will be able to move towards the plates, generating an electric current that can be measured. Conversely, when the mass starts to move away, the capacitance will decrease, the charge carriers will move away from the plates, and a current will be generated in the opposite direction. This type of accelerometer can be made in really small sizes, and therefore it can be used in all kinds of electronic devices. Although it is worth mentioning that since it uses air as the dielectric of the capacitor, if the capacitor changes its composition, so will its dielectric coefficient and the capacitance of the whole system. Therefore, in practical terms, the accuracy of these sensors can be affected by changes in ambient temperature or humidity. The next type of accelerometer we will discuss in this video is the piezoelectric accelerometer. This variation again uses a mass that moves when an acceleration is applied to the system. However, this time it will not occur completely freely, but its movement will be constrained by a piezoelectric material. This type of material has the quality of generating a small amount of electric current when it is deformed, either by being compressed or by returning to its initial state. Thus, when the mass moves, it compresses the piezoelectric material, generating an electrical signal, which can then be used to estimate the acceleration that was applied to the sensor, as in the capacitive accelerometer. The fourth type of accelerometer we will discuss is the piezoresistive accelerometer. These use, as the name implies, piezoresistive materials, which, when deformed, change their electrical resistance, that is to say, the ease or difficulty with which the electric current can pass through them. In one of the simplest versions of this type of accelerometer, we could have a mass connected to a fixed place by means of a beam, positioning a piezoresistor on it. When an acceleration is applied to the system and the inertial force on the mass causes the beam to bend, the piezoresistor will compress or expand depending on the movement of the beam.
Again, we know that this beam doesn't bend on its own. It requires an external cause, an external force, in this case being the acceleration, because that's what force is. And then that causes the displacement of this beam. And obviously that gets registered by this device and then gets turned into a digital signal, pretty much. But again, the principles are still the same.
Allowing us to measure the new value of the electrical resistance and use that information to indirectly estimate the acceleration. The great thing about this technique is that we can use more than one piezoresistor to estimate the deformation generated by inertial forces. In fact, we can use a single mass and 8 piezoresistors to make an accelerometer capable of detecting acceleration changes in 3 axes of motion at the same time. More specifically, we can position a mass attached by 4 beams to a base frame, also adding 2 piezoresistors to the ends of each beam. This way, each time the mass deforms the beams as a result of an acceleration, all electrical resistances change their value, and that information can be used to calculate the exact force and direction of the acceleration that was applied to the system. I'm not saying that this calculation is simple, but at least it's possible. The fifth type of accelerometer is the Hall effect accelerometer. To understand how it works, we must first understand what the Hall effect is. This occurs when we have an electric current passing through a conductor which in turn is passing through a magnetic field. One would expect the electric charges to pass through the conductor following the shortest path, a straight line. However, in reality, the electric current is distorted due to what is known as the Lorentz force. Because of this, a voltage that is perpendicular to the direction of the current is generated, also known as the Hall voltage. In other words, the Hall effect allows us to know the strength of a magnetic field based on the voltage generated. If we take this same system, attach it to a mechanical accelerometer and make the magnets face in opposite directions, we have everything we need to detect acceleration. When an acceleration causes the plate to move upward, a Hall voltage will be generated, and when the plate moves downward past the center point, another Hall voltage will be generated but with the opposite sign.
Again, the displacement and it's happening right here, with the mechanical device. This here is simply just detecting that displacement and registering it into a digital number, in other words. So again, same principles.
This is because the direction of the magnetic field reverses after that point. In this way, we can translate the magnitude and sign of the Hall voltage into the magnitude and direction of the acceleration being applied in this system. The sixth and last type of accelerometer we have left is the thermal accelerometer. This type of accelerometer has an extremely simple principle: to detect the temperature around a heat source. If we have a candle on a table in a closed room, the flame will remain relatively stable. However, when we move the candle, the flame will tilt in the opposite direction of the movement, due to the inertial force applied to the flame and the air resistance. What is more, its inclination will be proportional to the speed in which we move the candle. Considering this behavior, we could theoretically position 4 temperature sensors around the candle and use that information to estimate the direction of motion and the acceleration of the system. Clearly, in reality these systems do not use a candle. They are miniaturized, and work by heating an electrical resistor, but the idea is exactly the same. This accelerometer in particular is able to operate without moving parts, a quality that, as I have repeated 1,000 times, drastically reduces the chances of system failure, even during falls. Of course, not everything is perfect.
Again, it doesn't have any moving parts, but it still displaces the heat. When you accelerate this, the heat, it's going to displace, and that's how you're able to determine when there is a force. It's when the heat displaces. Not only that, depending on where the heat displaces, it's going to show you, it's going to tell you the direction that force is being applied. So again, even though this one doesn't have any moving parts, again, it still relies on the displacement aspects. Again, the principles of displacement when you accelerate. So yeah, no different.
This type of accelerometer, unlike many of the previous ones, requires a continuous source of energy to generate a signal.
All right, so let me just... Okay, so that was 6 different types of accelerometers, and the whole point of that video was to highlight how, regardless of what accelerometer you're using, they all rely on the same principles of displacement. So, for example, let me just... So again, this will be considered a simple accelerometer. Again, why? Because this air and water in a container like this, a water bottle, will detect acceleration. Regardless of what direction I accelerate, the water will always displace towards the back of acceleration, pushing the air towards the front. So again, this will be considered a simple accelerometer. Another type of accelerometer, again, similar to that, we'll be using an air bubble like this. Again, this will be an accelerometer again, because again, the air will displace in the direction of acceleration. So the air bubble, again, regardless of what direction you accelerate it, the air bubble will get pushed in that same direction. Again, not only showing when there's a force present, but the direction that the force is being applied. So again, these are the same principles of any other accelerometer. You know. So one more here. Again, the displacement of matter within a container that's being accelerated. Again, this will be considered acceleration detection device. This whole van, this whole with the apple and the helium balloon. Again, the displacement shows you the direction that the force is being applied. When I accelerate the van to the right, the air pushes the van pushes the air pushes the helium. So again, accelerometers again are devices that simply just detect acceleration. So okay, let's close this. All right, now that we got that out of the way, how accelerometers work and what they're used for, I want to get into optics real quick and how when it comes to determining if something is real or not, vision alone is not good enough. So I just want to go over this video again real quick, just to prove the point that vision alone cannot be trusted if we want to determine something is real.
Hey everybody, I've got some exciting optical illusions to go over with you today. You need to pay very close attention because your eyes are going to be trying to play tricks on your mind. And if you do focus well, you actually might be able to pick up on some of these illusions before I reveal them to you. This is furniture illusions. The reason I love optical illusions so much is because they play such crazy mind tricks on you. Take this chair, for example. Looks like your ordinary chair, except when I sit on it, the illusion is broken. And you realize that the camera set up at a perfect angle to make that one illusion work, when in reality, you sit this direction, and we've even had to curve the wood and mesh it in a way that, again, it's all about perspective from right over there.
So again, your perspective can easily be fooled. Again, when you're just relying on vision and vision alone, and you make a decision based on that, then, you can easily be deceived. You can easily fall into a lie that way, and again, vision alone should not be trusted.
So this next illusion, I'm going to show you how to make a floating, levitating chair. And this is the perfect time to tell you about our sponsor, Ashley Home Store. Thank you for powering the magic in this video. And they have a fun augmented reality app, actually, that works to preview the furniture. So I'm going to click this AR button, and you can see what it looks like in your home. You can move it around in 3D. But let's move on to the magic. I'm going to show you how to make this thing float. So this is the chair we're going to use for the levitation. First, I got to remove the legs. So now that I've got the legs removed from the chair, I'm going to set it down in the middle of the room. And now?
So again, if somebody was to show you this, a levitating chair, even in person, if you were obviously, it was presented to you, you would know that this is some kind of trick. Why? Because a floating chair like this defies physics. Again, unless the floor is magnetized and is able to push it up with some, magnetism. But other than that, again, that the chair on its own cannot be floating. So that this is some kind of trick. Again, why? Because this defies physics.
Got a levitating chair. Oh. Actually, it's just a mirror and some boxes, but still a pretty cool illusion. So this next illusion is created by a designer named Vivian Chow. And I absolutely love this piece. I call it the infinity illusion. And you might be wondering what kind of furniture it is. You want to take a guess? Now, if you guessed a chair, you'd be correct, but it's actually 11 chairs. Get this, each piece comes out from the smallest miniature chair all the way to the last chair, which is the 11th. Now, for this next illusion, we need to lose the light. Oh, sweet. So we're in this darker room to show off this next illusion with the 3 chairs. I want you to try to spot the difference between one of these chairs. One is not like the other. We have the green chair, the blue chair, and the red chair. Got your selection? I'm gonna reveal in 3, 2, 1. So the blue chair, if you watch it very closely, right now it's doing this weird, like trippy following the camera motion wherever it goes. And the reason it's doing that is because it's 3D printed and engineered in a way that it's actually pointing the opposite direction. So the illusion doesn't break apart until you get to see the other side. Trippy, huh? Let's move on to the next illusion. This is one of my favorite illusions. It's called an anamorphic illusion. And while technically it lies flat on the ground, it's one that comes alive when you line up the camera in the right position. This is called the 3-legged bar stool, and it's originally designed by a guy named Josh Carmody out of Melbourne, Australia. It looks like a 3-legged bar stool, right? But when I put my hand through here, it does this weird thing where the reason it puts my hand in front is because it's got a 4th leg right here. It's all about the design for the perfect perspective. So I hope you guys enjoyed furniture illusions, and if you did, you can subscribe right.
So again, just when it comes to vision alone, if you want to determine something is real, obviously vision alone is not good enough. So your vision can easily be fooled if you're just relying on vision alone. Again, if you have access, 3D access, and you have all your senses to determine something is real, then you're gonna figure out that whatever you're being shown it's a trick. So again, why is it important to understand how what accelerometers are and how they work? Again, because when it comes to observing something that's in motion, vision alone, again, it's not going to tell you what's in motion, because again, when you're relying on vision alone, your vision can easily be fooled. So again, when we're, let me go to this next video I wanted to present. See if I can show you this. Okay. So I wanted to share this video. Okay. So again, this video is going to highlight how when you're seeing something move in a particular direction from a particular reference frame, it can appear to move in one direction when it's actually moving in the opposite direction. So again, when it comes to motion, if you're just relying on vision, your vision can easily be fooled. Again.
Suppose you are traveling in an open car. Just for fun, you throw an apple out of it. Now you can observe an intriguing phenomenon. After hitting the road, the apple suddenly starts to follow you. How do you explain this crazy behavior? Let's get into it. When you hold the apple inside the car, it feels like the apple is at rest. However, relative to the road, the apple is moving at the same speed as the car. When you throw the apple from the car, you are in fact giving it a velocity opposite to its initial velocity. This opposite velocity reduces the apple's net velocity. The apple still moves in a forward direction, but with a lower velocity than the car, which means the apple will slowly move away from the car. Even after hitting the road, the apple will continue to have a forward velocity. So the apple has a forward velocity before and after hitting the road. Why do we feel like the apple was moving backwards before it hit the road? Here comes the trick our brain plays. Until the apple hits the road, the brain analyzes the situation in reference to the car. By that frame of reference, the apple has a velocity opposite to the car, the initial velocity you gave it when you tossed it. So you feel like the apple is moving backward. However, after the apple hits the road, your brain analyzes the movement of the apple.
again, visually, from your frame of reference, it looks like the apple is going backwards, visually. But physically, the apple is still moving forward. Again, it's because it's moving at a less speed than your frame of reference now. So again, because your frame of reference still remains at a constant, anything that's moving slower than that reference frame now is going to appear to move in the opposite direction. It's only going to appear to do that though, because physically it's still moving in the same direction you were moving, just at a slower rate. So again, your eyes can easily be tricked, but again, physics will show you what's really going on.
Apple in reference to the ground. Here, obviously, the apple has a forward velocity, and you feel like the apple suddenly starts to follow you. In short, this interesting phenomenon happens because your brain changed its frame of reference between you tossing the apple and the apple hitting the ground. This example is just an introduction to the world of relative motion and reference frames. Welcome to this interesting world.
All right, so I have another video here from Execrate. I'm not sure this one. So in this video here, again, when we're just relying on vision, again, we can't tell what's moving. So in this one, what would you say is moving? I know most of you have seen this already, but for anybody that's new to this, what would you say is moving? The background or the car? Not only that, what is moving and in what direction, I guess, will be the better question. So in this scenario, what's moving, the background or the car, and also in what direction are they moving? Again, let me play the next one. So in this one, you're going to see what was in motion. Again, I mean, it appears that the car is motionless and the background's moving towards the right. Or you can say that the background's motionless and the car's moving to the left. That's what it appears to be doing. It appears like the car's motionless and the background's moving to the back. So again, they were both moving in the same direction, except one was moving at a faster rate, giving the illusion that that the other one that's moving at a slower rate is moving in the opposite direction. Again, visually, that's only apparent. It's not physically moving to the right. They're both moving to the left, except one of them is moving at a faster rate. Again, giving the illusion that the other one's moving backwards. Again, so this was a great video showing a relative motion of two different reference frames. Again, same scenario, one more from Execrate. Share this down. Okay. Now in this one, he attached an accelerometer to both of these reference frames. Again, the liquid here with the air bubble. Again, by simply attaching an accelerometer to the reference frame, you will know whether it's the car moving, the reference frame of the car, or the background, without having to get the third, a third perspective of the two. Again, just by simply attaching an accelerometer, it's going to tell you what's moving. So again, you can see the air bubble in this scenario. This air bubble moved. So this reference frame was the one that was in motion in this case, because that's what physics shows. Physically, this is moving in this direction, and this background is not moving because the air bubble didn't displace. Again, visually, if we didn't have these accelerometers, it would look like this is motionless and the background's moving to the right, visually. But again, because we have accelerometers attached to both reference frames here, physically, we know that the car is moving to the left and the background was moving to the right. Again. Again, you clearly see the air bubble when this was moving. The air bubble got pushed in the direction of acceleration. This air bubble didn't move, so we know that it was the background that moved to the right, and this was motionless. The car was motionless. Again, when there's no accelerometers attached to the reference frame, again, we don't know what's moving. Again, visually vision alone doesn't tell us anything about when we're talking about motion and acceleration of different reference frames. Okay, so I'll just do one more. This was a video that I did. Again, using an accelerometer to determine what's in motion. I'll go ahead and play this one. This is the last one that I have for this presentation, and then we can talk about it a bit after. Okay. Go ahead. Stop sharing. Okay. Okay, so quick summary of that, I guess, is optics versus a physical. Again, when it comes to motion, optics alone cannot be trusted. So again, when it comes to detecting motion or acceleration, an accelerometer is what's going to show you what's actually moving. So again, when we're holding our phones, our phones have an accelerometer in them. We can use that accelerometer. Again, when we accelerate to the left, when we accelerate to the right, up or down, that accelerometer is going to detect the acceleration again, because that's physics. This is reality. However, in free fall, we don't get that detection of acceleration because an object is not being accelerated down. Again, that change in velocity that we experience visually, it's happening only optically, in the downwards direction, because physically, it's losing momentum, again, because there's no more force present. So it only appears to move in the opposite direction, again, because, we're still moving up, again, and something that's moving at a slower rate than the reference frame you're observing it from, it's going to appear to move in the opposite direction. So that's literally what we're witnessing. So let me see here. Let me just share a couple accelerometers drop tests that I did with the tube. Let me just do that real quick. Okay. So again, when we're comparing free fall versus actual acceleration, again. Okay. So in this one, I'm using a resistance band to actually accelerate this tube of water. Again, when I'm holding it and I'm connected to the earth, we can experience the displacement of matter. Again, the air bubble being pushed in the direction of the force that's being applied, which is up. And the steel ball is appearing to move in the opposite direction when I'm holding it. As soon as I release it, and the resistance band actually accelerates this container down, we get an inversion of this displacement. Again, because this will be considered an accelerometer, a simple accelerometer. So the air bubble now gets pushed in the downwards direction, and the steel ball appears to move in the upwards direction. But we know that the steel ball can move itself and the air bubble can move itself. So again, these are effects of a force, in this case being the resistance mat. So again, that's what happens when you actually accelerate down. You get the displacement of matter, as you should, Let me just go to free fall real quick. Which would be this one. Again, in free fall, we don't get the inversion of matter. The bottle, the air bubble doesn't detect the acceleration. It doesn't get pushed up or down. That's because there is no force acting. There's no acceleration at play. Again, if it was being accelerated down, we would see the air bubble also get pushed in that direction and the steel ball move in the opposite direction, which would be up. But what we witness here is the air bubble turns into a sphere because, again, it's not being compressed or pushed up or down, and the steel ball simply decelerates. Again, showing that it was in the upwards trajectory, and as soon as I release it, it starts to decelerate instantly. So again, real acceleration versus free fall shows you, that free fall is not acceleration. It's not accelerating. So I'm gonna see if I can open up let me stop sharing real quick. I'm gonna see if I can share, open the panel and share the link, see if anybody wants to join and maybe share their thoughts. Maybe, maybe you believe that maybe accelerometers work differently, or maybe, if you're a stationary flat earther, if you have proof of how objects can be accelerating down without displacement, maybe you can demonstrate some of that. So let me see here. Where do I go? see if I can post it.
Yeah, I haven't been talking just because I didn't want to ruin the presentation. So
No, yeah.
I'm not being weird.
No, yeah, I'm pretty sure people understand. Again, if you want to, add anything, just feel free. But,
I mean,
yeah.
it's self-explanatory, really.
Yeah. Let's see. So here's the link. If anybody wants to join, feel free. Okay, I'm gonna see if I could pin this comment. No.
Maybe it's just a start.
No, that's not. No.
Maybe I have to do it on YouTube.
Right. Okay, I may not be able to pin the comment, but it's still there for anybody that wants to click it. I'll be reposting it, I guess, every 5 minutes or so if it gets pushed out. But let me see. I want to see if I can try again. Okay. All right. So again, if everybody wants to join, feel free to click the link. But again, so I wanted to touch on the final experiment. Now that since we're talking about optical versus physical, because again, when it comes to the final experiment, the 24-hour sun in Antarctica, it only relies on vision alone, on optics. Again, at the end of the day, nobody knows exactly what the sun is, what it, how it works, the exact path over the Earth, So anybody making claims about what the sun's actually doing, to me, is just wasting their time. One thing to note, in my opinion, is, for example, we don't know the path that the sun takes, over the Earth, because nobody actually knows the exact dimensions of the Earth. So if we don't know the exact dimensions of the Earth, like the layout, for example, how can we know the path of the sun over the Earth? We would have to know the dimensions of the Earth first to then be able to start, observing the sun and then, making calculations. But again, at the end of the day, talking about the sun and what the sun is and how it works is a completely different discussion when it comes to establishing the dimensions of the Earth. So again, in my opinion, this whole 24-hour sun, obviously, in my opinion, is just a distraction. It's just there to basically, in my opinion, just to take the attention away from, real physics. The physics of water, for example, when contained at rest, always remain level. People claiming that it can, that the surface of water bends, again, the burden of proof is on you to prove that, and we understand that the physics of water, it's impossible for that to happen when contained at rest. So again, physics is just going to show us that the globe Earth is impossible. Why? Because a globe Earth, requires that you believe in this downward acceleration. Again, if it wasn't that the gravity was pulling objects towards the Earth, and it was the Earth actually pushing up and it was moving towards the objects, then that wouldn't work from a globe. So the globe Earth requires a downwards acceleration, which doesn't exist. So again, if we want to debunk the globe Earth, we want to do it physically, because again, the claim of the Earth's shape is a claim about our reality, our physical reality. So again, if we want to debunk the globe Earth, then we have to do it using physics, understanding physics. Again, looking at the sun and determining whether the Earth is round or flat, to me it's pretty retarded, at the end of the day. Like, again, it doesn't make any sense that people, would even take that serious, So it'll be, it's telling, so the people that are participating in this whole TFE thing, so, but it is interesting that, that apparently they are willing to fund a force the line experiment, which will be a direct physical measurement of water in specific. So, for example, I show these slides in my live stream. So let me just share them, just to give a kind of like a visual of what that experiment would be. Let me see, share entire screen. So again, the force the line experiment will be something similar to this. So building a level structure like this, and again having the structure, perpendicular to the initial plumb line here. So if we build completely 90 degrees perpendicular from this and remain that way, the further we go out over a body of water, if the water truly does bend at 8 inches per mile squared, like we're told, then that 8 inch per mile squared deviation should be there. It should be physically measurable. So again, in 3 miles, there should be a 6-foot deviation. So that means if the gap is at 5 feet when we first start, by the 3rd mile, there should be a 6-foot increase in that deviation. So there should be a 11-foot drop, for example, in this scenario. And again, if we extend this structure to 10 miles, that gap between the water and the level structure will increase to 66 feet from 5 feet. So that'll be, it'll increase 66 feet. So it'll be at, what is it, 66 feet plus basically 5 feet, which would be 71 feet. Sorry about that kind of brain farting there. So again, that should be measurable. It should physically be there.
But in my opinion, even the 3 miles is sufficient enough.
Yeah, 3 miles, 6-foot deviation should be there. Even at 2 miles, there should be a 2.5-foot deviation. So 32 inches. So again, physically, a physical measurement, of water would show that there is no deviation. So again, let me show. Here we go. See if I can. So again, this is what this is reality versus what people believe. I can't even move this. There we go. So again, this is physical reality. This is measurable, testable, repeatable. But again, this will be nice to have an experiment, again, a physical measurement of water to actually physically measure to see whether, water is level as in horizontal, or if water level actually means curve, So this will be the globe earth definition, which will be equal distance from the center to the outer circumference of a sphere, which will give you a curve, So that's what the force the line experiment would be. Again, a physical measurement of Earth, water in specific. And again, that should show, the deviation if the Earth is truly a globe. But again, at the end of the day, the globe Earth also requires a physical downwards acceleration again. So they're going to require an experiment that can also show acceleration without displacement, because that's what the claim is in Freefall. It's acceleration without displacement. So again, whatever people are claiming that this force is, causing this acceleration, whether electrostatics or, even if you claim that it's the ether or whatever, you're going to need an experiment again to show that you can actually accelerate a container without displacement. So, yeah. Let me see if there's any questions or anything in the
How do you
comments.
know if someone's like in the waiting room?
Oh, they'll just come up here.
Oh.
Yeah, so let me go ahead and post the link again since I'm having trouble pinning comment. Oh, no, it's still there.
Yeah.
Okay. Pretty slow today. So again, anybody wants to join, the link's right there in the stream. Again, if you think you can prove, you're a globe Earth or, stationary flat Earth or if you think that there's a more important topic than this to talk about, please join, and we'd love to hear. Because in my opinion, by far, understanding the reality we live in, again, Earth, is the most important topic, especially when people are believing the Earth is something that it's not. Again, when you believe the Earth is something that it's not, then by default, you're going to believe you're something that you're not. What it means to be human, So, I mean, if you could be tricked about something so simple as in objects not accelerating down and, Earth not having any convexity to it shown by water, then that shows that you can easily be tricked into believing anything, at that point, especially if it's concepts like concepts of living, like concepts of economy that we have, believe, everything you're told about it. For example, like, how much taxes you should pay, how much value money has, all of these concepts that are, people buy into. Again, it's all coming from ignorance. People not understanding things for themselves and just believing some kind of authority figure or an expert. So again, when it comes to, discerning for yourself, I think starting at the basics, is what's going to give you a strong foundation. PK, let me see if I can.
You just click what you're clicking.
I'm going to add you to the stage. I just hope you're not a troll.
You can just click on it.
But hey, how's it going? Can you hear me?
Hey, William, how you doing?
Hey, I'm doing good. How are you?
I'm well. Love your videos.
I appreciate that.
But I haven't seen many of them, so I've got a few questions. If you can elaborate on some of the ideas.
Sure. What are your questions?
So the Earth is moving upwards is it accelerating upwards or moving upwards at a constant speed?
So the Earth is moving up at a constant speed. And how do we know that? Because again, if we actually accelerate or up, our weight will increase. So again, if we continue to accelerate, then our weight's going to continue to increase. So the fact that when we're standing on Earth, our weight is constant, that shows that the force being applied is a constant as well.
But if you get in a car and you drive along the road at a constant speed, you don't feel a constant force at your back.
That's because the car's connected to the Earth. So it's already experiencing a force.
All right, what about an airplane? When I fly in an airplane at 700 kilometers an hour, I don't feel like something's pushing from behind me.
Yeah, same thing. When you're flying an airplane, you're flying level. The air's pushing up on the wings.
No, William, you're not understanding what I'm asking you. You're saying that the Earth is moving up, and that's why I feel weight, right? That's why I feel like there's something pushing from below me. But when I'm flying in an airplane at 900 kilometers or 600 miles an hour, I don't feel anything pushing me from behind. What's the difference?
There is no difference there. The airplane.
Well, there is a difference. You're saying the Earth is moving at a constant speed upwards, and a plane is moving at a constant speed sideways. But here on Earth, we feel this force upwards, but on a plane, I don't feel a force sideways. Why not?
You feel the upwards force on a plane because the motion transfer of the Earth pushing.
No. I'm not saying the upwards force, William. I'm saying the sideways force, because a plane is flying sideways, isn't it? Right? It's moving forwards along the surface.
All right, let me explain. So in a car, and I'm going to go from the car first, and then I'll go to the airplane. So on the car, when you're connected to the Earth, you're experiencing that upwards push because it's physically connected to the Earth. So you're having to overcome that force to get the acceleration, the pushback effect, because you're having to overcome the force. When you're on an airplane and it's flying level, it's also experiencing that upwards force of the Earth through the air, because the air is also being pushed up. So you're having to constantly accelerate. If you're not accelerating the airplane, you're not going to feel that pushback. Just like
William, you haven't understood my question. No, let me make it a bit simpler. Right now,
Sure.
you're sitting in a chair, yes, in your room.
Sure.
Okay, and apparently we're moving upwards, right? So the chair is moving upwards at a constant speed. So that's why you feel pressure on your bum, right? Pushing you upwards to support you. That's why you feel like you have weight. True?
Sure.
Okay, now in an aircraft, imagine you're in that same seat moving horizontally in an aircraft at 600 miles an hour. Why don't you feel pressure from the back of the chair pushing you forward?
Because if you're moving at a constant 600 miles an hour, you're not overcoming the upwards push of the air that's being created by the Earth. Same scenario like the car.
Air's got nothing to do with it, William. You're in an aircraft.
Yes, it does.
The air is not rushing. You're inside the aircraft, William.
But the aircraft's being pushed up by the air.
What gives the airplane rise?
No. But why don't you feel a horizontal sideways force from the back of the chair if the aircraft is moving at a speed horizontally?
Because you're going to have to overcome the upwards force, the buoyant force of the air pushing up on the wings.
William, that's got nothing to do with it. That's got absolutely
everything to do with it.
We're talking about a horizontal motion. You're claiming that the Earth is moving up in a vertical motion, therefore you're feeling a force from below, right?
Let me ask you this. Do you believe the Earth is
William?
No, let me ask you. Because
I don't think you're understanding the question clearly enough.
Let me ask you this. I want to know your stand. I want to know your stance. Okay, so do you believe objects accelerate down towards the Earth? Yes or no?
That's irrelevant. I'm trying to understand your theory. You're the one explaining your ideas, right? So I'm just trying to understand your ideas. What I believe isn't the issue here. You're the one putting your theory forward. So
it's not a theory, it's demonstrable physics.
William, and for the listeners that are watching right now, the viewers, I want to make this very clear. You're stating, I'm steel manning your argument here. You're stating that the reason why your chair is able to support you is because the Earth is moving upwards, and therefore you're feeling a force from below you, from the chair, holding you up. True? Giving you that apparent feeling of weight because the Earth is moving upwards. So you're feeling the force from the bottom of the chair, which is moving upwards at a constant speed, right? That's the key, constant speed. But in an aircraft or a train or a plane or anything else, if you're moving horizontally at a constant speed, as you do in an airplane, why don't you feel the same force from the back of the chair?
Again, because when I'm just sitting here on Earth, it's just one force that I'm feeling. If I want to feel the force in a different vector, then I'm gonna have to overcome that force. And in order to overcome a force, you need to constantly accelerate. So in an aircraft that's moving...
William, that's word salad. Your words didn't make any sense there. That doesn't make any sense.
One force is stronger than the other.
Yeah, in order to overcome a constant force, you need to constantly accelerate. So when an aircraft is flying at a constant speed, being pushed up by the air, it's having to overcome that upwards push, which is a constant. So that's
what about the horizontal motion, William? The horizontal motion.
If it's a constant, and then the upwards vector is affecting it, then you're going to have to overcome that.
Why is there no horizontal force when the plane is moving horizontally?
If the airplane didn't have any wings and it was in free fall and you were moving horizontally, you would feel constant pressure behind you if it was in free fall moving forward.
I think you're a little confused about this issue, William.
I think you're confused.
I made this as clear as I can. You're feeling an upwards force because you're claiming the Earth is moving upwards, but we don't feel a sideways force when an aircraft moves sideways. So I think I've just debunked your key principle, your key argument. Okay, let me ask you another question. When I hold a glass, an empty glass, and I let it go, you're saying the Earth moves up to catch up with it because it slows down.
Exactly.
What's slowing it down?
Inertia. The matter has inertia, so it resists motion.
So the object wants to. So you're saying that inertia is what? A tendency to stop moving?
It's a resistance to motion.
So objects always want to come at rest. Is that what you're saying?
In this reality, yes.
Why is inertia, as all scientists understand it, resistance to change in motion and not resistance to motion?
It's resistance
Do you know the
to
difference?
motion.
Do you know the difference between the conventional definition of inertia? Do you know what the conventional scientific definition of inertia is?
What's the conventional definition of inertia?
I just said it. It's resistance to change in motion. So an object that's already moving wants to keep moving. That's like when you go ice skating and you push away because you have very little friction, you keep moving.
That's in a frictionless environment where there's no thing in a vacuum. We don't live in a vacuum. So matter has inertia, meaning it always wants to remain motionless, whether constant or change.
But why does an ice skater tend to keep moving? And if you have an air puck table, an air hockey table, the puck keeps moving because there's very little friction. So if you remove friction, objects tend to keep moving. That is actually inertia.
Yeah, you can add more resistance to inertia and make it slow down faster, but matter still wants to remain motionless.
Are you saying things don't lose momentum?
And they do if there's resistive forces present. But if you take away those forces, if you reduce friction, objects will tend to keep moving, won't they?
But they won't go forever. That's the point.
The less friction there is, the more they tend to move, though, right?
Yeah, but they still won't move forever.
Okay, so here's my next question, William.
So let me ask you a question, because you're asking all the questions here. No, let's go back and forth, because that's how a conversation goes. You ask me a question, then I ask you a question,
give me a
then
question.
you can ask me a question.
Go
Okay,
ahead.
so do you believe objects accelerate down in freefall?
Yes.
How do you justify that belief?
Because there's a gravitational force acting on all matter, and the force is directly proportional to the mass. Therefore, the acceleration is constant.
Okay, so that was word-sided. Wait. Okay, do you have a practical demonstration of this kind of acceleration that you just
Yes,
claimed?
I can explain your demonstrations, William. I can explain those demonstrations.
No, but do you have no, I'm not asking for an explanation. I'm asking for a demonstration.
William, I can explain why the water doesn't displace.
No. I'm talking about demonstrations here. Do you have a demonstration of that kind of acceleration?
What kind of demonstration do you want?
So you're in free fall. You're claiming that gravity accelerates all matter equally, so that way it doesn't displace. Okay, so do you have a practical demonstration of this kind of acceleration in any other vector other than free fall?
Well, what other force? I could do that actually. If I have a magnetic field or an electric field, William, because those are non-contact forces, just like gravitational. And if let's just use magnetic. If I have a jar of nails in a magnetic field and I turn the magnetic field on because it's electromagnets, I will guarantee you all of those nails will move at the same rate.
Okay, I agree that magnetic.
Do you agree that that would happen? Do you agree that that would happen?
Yeah, I agree that will happen. But what I'm asking for
is,
can you explain? No. In free fall,
for gravity, William, it's exactly the same principle for gravity.
No. In free fall, you're claiming no. In free fall, you're claiming that solids, liquids, and gas can accelerate and be affected by gravity equally. Now you're telling me that magnets can affect nails, but can it affect liquid and gas as well equally?
Well, we're not talking about gravitation. I'm talking about magnetic force.
Okay,
gravity is a unique force.
Okay, why did you jump from gravity? Why did you jump from? I asked for a demonstration of gravity, not magnets. I asked for a demonstration of gravity, not magnets. Okay. So you're irrelevant then.
William,
that example is irrelevant.
William, unfortunately, it's very difficult for me to travel to another planet with a different gravitational field and perform an experiment for you. You know this full well. So
you can't demonstrate it here on Earth then, is what you're saying?
Not easily. Not without a rocket ship, not without Elon Musk's help, no.
So I'm just supposed to believe that what you're claiming
you've seen
is true?
footage. Listen, you've seen footage of astronauts on the moon dropping a feather and a hammer, and they both fall at the same rate. Have you seen that footage?
How do you know they're on the moon?
Okay, how do we know that anything is real then? How do we know we're not in a simulation? At what point do you take off the
fire and tell me if you get burned?
William, you're talking about a gravitational force that we are all surrounded by. Any experiment
I'm not talking about that. You're talking about
that gravitational field. What you're asking for is beyond practical reality. It's beyond
it's all fantasy. Exactly. Your own words. It's fantasy. It's beyond our practical world because it's not real.
Okay. My turn for a question, William. I answered your question. My turn. So there's some material that's slowing objects down as they lose inertia, right?
No,
Well,
I wouldn't say it's some kind of material. I would say it's more like a background medium that affects all
okay,
matter.
good. What is this medium?
I don't know. It's up for investigation. I have
And why
no
does
clue
it
what that
affect?
is.
Okay, why does it affect all objects of different density equally? Which is not
It's
how
just
things
what it
normally work.
does.
It's not how
It's just
things
what it.
normally work. Oh,
Why is fire hot?
you don't know why. You don't know what it is, and you don't know why it does that.
That doesn't dismiss the
And
fact
why
that
is it
buoyancy.
9.8? Okay, William, here's another question for you.
Sure.
Why
sure.
is it?
And then I'll have
we
a
can-
question for you after.
Okay, William, we can measure the precise rate of that acceleration, can't we? Right, 9.81 meters per second squared is the average value on Earth. However, we know that it varies slightly at different positions on the Earth. Now, a ball Earth,
So-
you can explain that because the Earth has slightly different radius and different densities, whether you're near a mountain or not. But you cannot explain that because the whole Earth is moving up at the same speed, isn't it?
So the 9.8 meters per second acceleration first that you claimed here, that's only a change in a change of rate, a change in velocity that we witnessed.
That's right.
It's
That's
not-
what acceleration is.
So
Yes.
measuring so changing a change in velocity of a free falling object doesn't tell us whether the object is accelerating down towards the Earth or the Earth is moving up towards the object from the constant. So how do you determine that it was the object accelerating down towards the Earth? Because it could be either or.
Okay. Listen, you're saying that some medium is acting as a resisting force, slowing the object down, right? That's what you're saying. But I'm asking you, how can this medium affect all objects of varying density equally?
That's just what it does. That's what we witness.
We can
That-
You
demonstrate.
don't know what it is, and you don't know why it acts that way.
It's up for investigation. I will admit to that. So it's something that's still obviously, it should be
back
questioned.
back to my previous question, William. Why does the rate of acceleration change at different parts on the Earth? 9.79, 9.81, 9.80. Why is it different at different parts of the Earth? If the Earth is one object moving upwards at the same speed.
Okay. So I have so I have to double check that to make sure that that's true. Because I have
You do
heard
know
that
that's
claim.
true. Come on, that's well known
I've heard that
information.
claim before that.
The rate of
there's different
acceleration
acceleration rates on it. So
does vary.
my simple answer. Okay, sure. I would say this doesn't prove whether what's moving up or down in my opinion, but I'll tell you my opinion on that, and it's simply because the Earth is not moving in a straight line. So that's why, in my opinion, there will be slight differences in the accelerometer.
But William, if the Earth wasn't moving in a straight line, objects wouldn't fall down. They'd fall at different angles.
Relative to us, it's moving up. It's not
But if the Earth is not
gradual.
moving in a straight line, then objects would move at some angle, fall at some
No,
angle.
not relative to us within it. Not relative to us within it. The time that it takes for the object to decelerate and the Earth catch up to it, the object will be it will appear to us as linear motion.
Man. Come on, that doesn't make any sense.
Well, again, that's my answer to your question when it comes to that. So let me ask you this. What was the
Sure,
question? Okay.
sure.
Okay, so let me just share this real quick. Let me share my screen. Okay, let me share my screen here. So I can recreate so here, can you see my screen?
Yes, I can. Oh, you got the balloons in the van. Yeah, I can see that.
So again, I can recreate buoyancy in a container by simply accelerating the container in a particular direction.
Okay, hang on. Can I just briefly interrupt you there? Here we go.
Sure. You have a question?
At the equator, acceleration is 9.83, but at the poles, at the North Pole, for example, it's 9.78. William, that's your homework. You got to figure that one out for us, okay?
Sure, I already gave you my answer to that, but okay, going back to this.
But that answer didn't make sense.
Buoyancy.
Okay, go tell us.
Right, measurable, testable, repeatable. Buoyancy is an effect of a contained system that's in motion, and relative to the direction of the motion is what's going to displace the buoyant object in that direction. So in this example, I push the van, accelerate the van to the right, which is moving the air with it to the right, which is pushing the helium balloon to the right. So if
Well, no,
if
that's
I
not the
can,
full explanation, William. You didn't explain it clearly there. You didn't explain it.
yeah, okay, let me explain it again. So when I accelerate the van to the right,
Yes.
the air that's inside the van is being carried by the van in the same direction. In other words, it's being
Yes.
pushed with it.
Yes.
So the air is more dense than the helium, so it's also able to push it in that same direction. So the helium reacts to the air pressure.
You missed a crucial part of that explanation.
You tell me what's happening here, then. You tell me.
Okay,
What's
let me explain what's happening. First of all,
You
let's
tell me
deal
what's
with the solid red ball at the bottom, right? Which is obviously a heavy mass. As you move
Sure.
forward, inertia, because it's
Exactly.
stationary, it wants to remain stationary, right? So therefore,
Sure.
it stays in position as the van moves to the right. Okay, so
Sure.
that's easy to understand. That's
Sure.
pretty simple. Now, the van is full of air. Now, what is air, William? What is air made out of?
You tell me. I mean, we have concepts
You don't
about what
know?
air is. We
Hang
have
on,
concepts.
this is not a trick question, William. This is not a trick question.
It's a gas.
It's a gas.
It's a gas.
And what is a
Yes.
gas? Gas is made of what?
You tell me molecules?
William, molecules.
So we're going into imagining little balls. Okay, sure.
Well, what is a gas, William? What is it?
Nobody knows what a gas is.
William,
it
William,
is what it is. We have concepts.
It's matter, though.
describe-
Isn't gas matter?
Sure, yeah, it's matter. Then you can ask, well, what is matter? And again, we can ask this question. At the end of the day, nobody knows exactly what matter is.
Okay, but our best understanding is that it's atoms, right?
No, that's just no. I would say that's
carbon,
completely off.
oxygen, nitrogen.
Yeah, but to say that they're little balls, little atoms, I would say that's full of shit.
Well, what is matter then?
Again,
What are you
nobody
made of?
knows.
William, what are you made out of?
I can be honest and say I don't know.
But
I can actually be honest and say that.
You don't know what you're made out of, William? You don't know what you're made out of?
I mean, I'm made out of skin and bones. I mean, we can give these labels, sure, but what is it actually? Nobody actually knows. You have to be the creator to know.
But William, we have so much evidence that allows us to understand the difference between solids, liquids, and gases, and
Sure,
the fundamental
Yes.
the particulate nature of that matter. Okay, let me explain what's happening in the van, William. Let me give you my explanation, which is the well understood, logically coherent scientific explanation. The van is full of gas, right? Air, mostly nitrogen, 78% nitrogen, 21% oxygen molecules. Now, those molecules are normal matter, just like you, just like your girlfriend, just like your chair, but they happen to be separated as a gas, right? There's space between them. Now, that gas also has inertia, just like that solid red ball at the bottom there. Now, when the van starts moving, the gas wants to stay in place. So it all bunches up towards the left, the back of the van. It compresses at the back of the van. Now, when it compresses, it becomes more dense on the left-hand side. And a pressure gradient builds from the left to the right. And because it's more dense on the left-hand side, it pushes the balloon towards the right, because the inside the balloon is less dense than the increasing density of gas on the left-hand side. That's what pushes the balloon forwards.
Exactly. So a pressure gradient created by the motion of the container in this case, right? So
which as I said, bunched up the gas molecules towards the back of the van.
I would say that those are the exact same principles that we experience here on Earth when we release a helium balloon and it moves up. It's the air that's being compressed by the Earth's motion that's pushing up the helium. So exactly.
William, what's causing the pressure gradient in the atmosphere?
Here on Earth?
Yeah.
The Earth's motion. And because, like you said, air has inertia, it wants to remain where it's at. It compresses, when the Earth pushes up on it, it compresses, creating a pressure gradient that we have here on Earth. And that gives us our buoyant effect of helium balloons rising through it. It's the air that's pushing. It's the same principles.
But you don't even know what air is. So how do you even know what a
Nobody knows what air is. Again, you just gave me a description of what we think.
Your answer uses my model of particles of air.
Well, matter is made up of something. I agree. So whatever that something is, it's what's compressing. You want to use atoms and molecules, fine. But I don't buy into that concept.
You just use
matter is made up. Matter is made up of something. I agree.
Okay, so what was
I don't know what difference that makes.
with this experiment, the video that you
That
showed me?
buoyancy is the only cause for buoyancy. It's a container that's moving, and relative to the direction the buoyant object moves, is the direction that the force is being applied or the motion's happening. So the motion is up, shown by helium balloons. So my question to you would be, if you deny that buoyancy is a cause of a container that's in motion, what's the mechanism for buoyancy, if not push?
Because gravity is pulling air molecules down towards the ground, creating that pressure differential.
So you're claiming that the air's being pushed down, but it's the air's
not being
pushing
pushed
helium
down,
up.
it's being pulled down
So
by gravity.
What is pull? What is pull?
It's an attractive force. Oh, you don't. Oh, that's right. You don't even think that there are pull forces. You think that forces only push, not pull. Is that right?
Exactly. Yeah. Can you
what
demonstrate a pulling force? Can you demonstrate a pulling force?
What happens if I bring the North Pole close to the South Pole of a different magnet? What happens?
There's a flow that happens between them.
Hang on. You can't get away with saying flow, William. What's the other F word? What does the North Pole do to the South Pole?
You tell me.
It attracts it, doesn't it? Which is a force of attraction.
So mechanically, what's happening between the two poles that makes them come together? What's happening mechanically?
Well, magnetic fields are incredibly mysterious. We don't understand.
Exactly.
But you have to admit that that's an attractive force, though, right?
It's definitely some pressure going on there that affects metal.
Okay, William. I'll give you another one. Listen, William. I'll give you another one. If I take a sheet of plastic and I spray water underneath it, the water drops stick to the plastic underneath. Are they pushing on the plastic or pulling on the plastic?
I would say that they're being pushed somehow.
No. But William, they're hanging off the plastic. Are they pushing towards the plastic or pulling down off the plastic? There's
obviously something going on there.
Is it push or pull, William? Push or pull?
Well, pull doesn't exist, so it has to be some kind of pressure.
So you're saying that water droplets are pushing upwards towards the plastic, or are they pulling down on the plastic?
Like I said, pulling forces don't exist, so it would have to be some kind of pressure.
See that red mass in your video on the string? Yeah. Is it pulling down on the roof of the van or pushing up on the roof of the van?
It's resisting the upwards motion, so it's pushing down in the opposite direction of the force.
Is it pulling on the van where the string is attached to the van? Is it pushing or pulling on the van?
It's resisting the motion, so it's pushing back. It's pushing back.
William, come on, it's really not that hard. It's really not that hard, William.
It's really not that hard.
It's pulling down on the roof of the van, William. Come on.
So you're claiming gravity is pulling the air down, but somehow the air is pushing helium up in the opposite directions being pulled.
Because of the different densities. William, why does a boat float on water?
Oh my God! Because Earth is pushing up the water, and then that water's pushing up the boat.
Why doesn't the boat just go straight down through the water?
Well, again, if it's buoyant, then the water's going to be dense enough to push it up.
Well, there's your explanation. That's the same explanation to what you were just giving.
Yeah, but the water is moving also in the upwards trajectory, making that upwards push. That's giving the boat its buoyancy. You're claiming the water is being pulled down, but it somehow is able to push up. I just think that's really funny.
William, do you know what Newton's third law?
No offense.
William, do you know what Newton's third law is?
Yeah.
What is it?
For every action, there's an equal and opposite reaction.
And what does that mean exactly?
Well, that means that, again, when you push an object, you're going to get an equal opposite reaction to the resistance to that motion.
An equal and opposite force, William, an equal and opposite force. So
I would say that's the inertia.
When a boat sits on water, it pushes down on the water, and the water pushes back up with the same force.
The water's pushing up the boat, and the boat's pushing down because of inertia. Exactly.
Providing buoyancy.
You just said it backwards there. The boat's not pushing down first. It's the water pushing up on the boat, and then the boat pushes down in the opposite direction because of inertia.
Okay, that's the other way around. If you believe that the Earth is moving upwards, however, that's just not what the case is, William. And listen, let's go to a fundamental problem with your theory, right? A fundamental problem. you think that constant motion produces force because the Earth is moving
Yes.
upwards at a constant speed. Yes.
Yes.
Okay. So I want you to do a very simple experiment next time. I want you to get a skateboard and a scale, like a bathroom scale that you stand on.
Sure.
Okay. Now, if you place the scale vertically on the skateboard and you put, let's say, a bowling ball in front of it and then pull the skateboard at a constant speed, do you think the scale will register a force? According to
Sorry, can you repeat that one again? I'm sorry.
So we take a skateboard and we put a bathroom scale on it vertically, right?
Okay.
Because we're going to pull the skateboard along a flat surface. And we put a bowling ball in front of the scale. And then we pull the skateboard. So the scale will move forwards with the bowling ball.
Okay, so you're seeing the skateboard like this, and then the scale like this.
Yes,
vertically,
yes,
right?
yes,
Okay.
yes. And
Okay.
you pull it to your left with a bowling ball in front of it. Now, if you pull it at a constant speed, you're saying that there'll be a force applied on that bowling ball, which we could measure on the scale. True?
Yeah. So the constant speed, again, if there's no other forces acting on it, then a constant speed will give you a measure. But if there's a constant force already
I want you to
acting,
do
you
that
have to overcome.
experiment. I want you to do that experiment. That's a very easy experiment to do. But you need to pull it with a constant speed. That means you need to connect it to a motor that has a constant RPM to provide a constant speed.
But again, if that skateboard's connected to the Earth, then in order to get a weight measurement, I'm going to have to constantly accelerate to create that new vector.
No.
That's what you're asking. You're asking me to create a new vector.
No. That goes against your theory. You're saying that a constant speed produces.
If there's no other forces acting, then yes, a constant speed would. But if you're connected to the
those
Earth,
two forces, William, the two forces we're talking about are acting perpendicular to each other, so they shouldn't affect each other. We're just talking about the horizontal motion.
Yeah, but if you're connected to the Earth, you're experiencing a force already, and in order to overcome a force, you need constant acceleration.
You know that this
it's
is
the same airplane question, but just with different. You're asking the same airplane question, but just with a skateboard.
Okay, explain to me why the gravitational force will affect the horizontal force.
The gravitational force will affect the horizontal force?
Yeah, you said because the skateboard is attached to the ground. Okay.
Yeah. So it's experiencing that upwards motion already. So it's in motion already.
Why does that affect any force acting horizontally?
Because it's always there. So you have to overcome it if you want to create a new vector. Wait a minute. It's a constant.
William, those are two separate forces, one pushing up and one pushing sideways. One does not affect the other.
Oh, well, it does. If you want to overcome
how does one affect the other? Okay, William,
one doesn't affect the other. I'm not saying, one doesn't affect the other. But if you want to if you want to create a new vector and there's a force present, you need to overcome that force with constant acceleration.
Okay, William, don't talk in generalities. Talk about this specific situation. Talk about the skateboard moving horizontally across a floor. Why does the Earth moving up affect a horizontal force that would be acting?
It affects it because, again, if you're moving at a constant horizontally, there's always an upwards force when you're connected to the Earth. Again.
Yeah, but we're not measuring the up. We just want to measure the horizontal force with that scale that we put on the skateboard.
If you want to do that, you have to do it in free fall. Having the scale on a free falling object and then with some thrusters or whatever, accelerate it forward at a constant, and you will get what you're asking for in free fall.
William, you haven't explained why the vertical will affect the horizontal.
I told you, because in order to recreate a new vector, if you're already experiencing a vector, you need to overcome that vector. I don't know how more simple I can get.
Okay, William, let me tell you something. If you actually accelerate that skateboard across the floor, then you will get a reading on the scale. But if you move it at a constant speed, then you won't. This complies with conventional science, not your explanation. It complies with conventional science.
When
and we
connected to
understand
the
that
Earth.
very well. Because inertia, like I said, is a resistance to change in motion, not motion itself. And the skateboard experiment would prove that to you if you conducted it.
Again, it's the same question you asked with the airplane. Again, in free fall, when there's no forces acting, when there's no vector, then a constant velocity would create this new vector of weight and orientation. So again, in free fall, if you start moving in a particular direction, then you will get that compression at a constant because you're not having to overcome the force.
So you're saying that if we could do this experiment in free fall and we moved it horizontally at a constant speed, there would be a force registered on the scale. That's what you're saying?
Yes.
I think you're wrong. I think you're incredibly wrong there.
Okay. Well, I guess that's just your opinion. But again, at the end of the day, whether you believe the Earth is a globe or a stationary flat Earth, you require a physical downwards acceleration, which just doesn't exist. All practicality, accelerometers, whether digital or analog, show that there is no physical acceleration down in free fall. And buoyancy shows that it's the Earth's push that's creating that effect.
Okay. Listen, you know what, William? Why haven't you put all these ideas on paper? Why haven't you published something?
Why would I waste my time doing that when I can easily just go online and speak to a bunch of people and share these experiments visually? Why would I waste my time writing a book?
This stream explains exactly why you should write it down, because we've had a pretty decent discussion. I mean, I've spoken to you at a pretty, high level. You've answered me back at a high level, but we haven't been able to agree on a set of facts that make a coherent model, a coherent theory. So I would really, because listen, what I'm saying is in books. It's in thousands of books. You can go to any library and read everything I'm saying in any textbook, high school, university level you want. But I get nothing to read from your side of the argument. I've got nothing to get a positive grasp on the ideas. So I would really, really appreciate if you just, it doesn't have to be a book, William, a pamphlet, a couple of pages with a few equations and a coherent, logically explained model of what you've been going on about, because you spend so many hours making videos and sitting at university campuses talking to freshman uni students who don't really understand this stuff. Put it on paper, William, so that we can have a much clearer understanding. And you know what? I don't think you can do that. And let me tell you why I don't think you can do it, William, because you don't have a clear picture of what you explain.
Okay.
You don't have
you have all these
consistent understanding.
Sure. So you just told me that you can research all of this information. There's books everywhere, right? Well, I have reality. I have practicality to show my claims. I'm not just making these claims.
This is what I'm saying, William.
I have demonstrations.
If it's so obvious and easy for you to understand, put it on paper for us.
I'm not the type to write books and all that. I'm not really into that. So again, if somebody else wants to do that, then they should do that. That's not going to be my route.
You have a very unique take on this. No other flat earther talks about a constantly moving upwards Earth. Some of them,
there's a lot of other people.
Who else talks about a Earth that's moving upwards constantly? Who else? Give me one name.
I'll name a few. Del from Beyond the Imaginary Curve, Andrew Execrate, Nachiqueta, just to name a few. Execrate 200. Yeah, Execrate 200, Andrew. He does a lot of experiments on his channel. Again, this is just a few, and the number is growing. Again, there's going to be different kinds of people that are into different, kinds of things that are going to get into this topic eventually, and maybe somebody will write a book, and maybe then maybe then you'll grasp it, huh?
Here's the problem, William. When there's different people talk about different things, you guys don't have a consistent model that works, that can answer all the questions.
Reality is not a model. Reality is not a model.
Okay, well, theory then. Let's call it a theory. Your theory is different to lots of other flat Earth theories. And if you're so convinced that your one is right, justify it. Put it on paper. Explain the ideas and make them logically consistent.
I mean, I am demonstrating my position.
You're doing it very piecemeal, right? It's a little bit here, a little bit there. And when I ask you specific questions, the logic falls apart and you can't actually explain it. The skateboard question, William. Vertical forces do not affect horizontal forces. That's my position. You're saying they do. You're saying they do, but you can't tell me how.
I did tell you how.
Or
because
why?
Again, when we're connected to the Earth, we're having to overcome that constant force.
Why though? What's the logic behind that? You just made a statement. You didn't make an explanation. Explain it.
Because in order to overcome a constant force, you need constant accelerator. To create a new vector, you need to constantly accelerate from the constant to create a new vector.
To create a new vector, you need to constantly accelerate from the constant. That is just the most vague statement I've ever heard, William. That doesn't
from
make
the constant force that you're experiencing on Earth.
Okay, listen, apply it to my situation with the skateboard. Give me that same answer specific to the skateboard experiment.
I mean, it's the same thing. If the skateboard's connected to the Earth,
give it to me with vocabulary around that experiment.
What do you want me to tell you?
Why, when I pull a skateboard horizontally at a constant speed, will the scale not register any force on the bowling ball?
Because the skateboard's connected to the Earth and it's already experiencing a constant force. And
but that force, according to you, is upwards. I don't care about the upwards force. I'm talking about a horizontal force because according to you, any constant motion produces a force on a body, right? That's
when
what you're saying.
It's just one force? Yeah, when we're just dealing with one force, yes.
Hang on, William. The Earth is moving up. That's why everything gets pushed upwards.
That's one force they experience. Yeah, and then when you accelerate the skateboard on Earth, that will be a second force you're introducing.
William, I'm not talking about accelerating the skateboard. No.
When you're okay, let me ask you this. When you're
William,
pulling,
hang on.
Let me ask you this real quick.
Super simple. I'm going to give this one more shot, William.
Sure.
The Earth is moving up at a constant speed. Therefore, we all get pushed up with the Earth. Now, if a skateboard moves horizontally at a constant speed, why wouldn't the bowling ball experience a force as well?
Okay, when you're pulling the skateboard when you're pulling the skateboard at a constant speed,
yes.
Yeah. Let me ask you this: is that skateboard only experiencing one force, or is it experiencing two forces?
There's an upwards force because the Earth is moving upward, according to you, but it's because of gravity.
No, even if you believe in gravity, even if you believe that it's a downwards pull or it's force that's pulling things down,
there's a vertical force upwards.
When the skateboard's being moved horizontally, is it experiencing one or two forces?
There is if it's moving at a constant speed, it's only experiencing one force upwards.
It's only experiencing one force.
Yes, but according to you, it should be experiencing two. It should be experiencing a horizontal force as well.
Exactly. So again, in order to overcome that
so
initial
let's do the
force,
experiment, William. Let's do the experiment and see if it does.
Again, in free fall, like I said, the constant would create that weight because there's no other forces it needs to overcome.
You can't tell me why it has to be done in free fall, though. You can't tell me why.
Yeah, I told you because there can be other forces acting on it. Because if there is, then you have to overcome that force.
William, but those forces are acting in different directions. It doesn't matter if they're in different directions. It would only matter if they're in the same direction because they would cancel each other out. Perpendicular forces do not affect each other.
They obviously do.
Give me an example.
With the acceleration, you could add liquid into a bottle, and in order for it to displace that liquid, you need to constantly accelerate when connected to the
William, we're talking about perpendicular forces. William, if I push you from the left-hand side and someone pushes you from the right-hand side and we both push with the same force, those forces would cancel out. Don't you agree? And you wouldn't move anywhere, right? You wouldn't go anywhere.
Sure.
Because they're in opposite directions. True?
Sure.
Okay. But if I pushed you from the left and someone pushed you from the front, you would go flying off in some diagonal direction, wouldn't you?
I believe so. I mean, sure.
Right? Yeah. Okay. So what that shows you is that the forces that are opposing from opposite directions are the ones that affect each other. But perpendicularly, you would have both horizontal and vertical motion and whatever else. So the vertical force produced by the Earth should not affect in any way the force produced by the skateboard moving horizontally along the floor.
Again, it should, because again, you're having to overcome the constant. So I feel like we're just going in circles. Do you have anything else
have to overcome the constant, William? The
constant force of the Earth.
Any sense?
The constant. Okay, when you're standing here on Earth,
William, you're wrong. You're wrong.
William, is gravity
wrong? William, you said you would have to overcome the constant force of the Earth, but the Earth's providing a force up and down. So to overcome that would mean pulling it up.
If you believe the Earth is a globe, then yeah, the Earth is causing a force up and down. Again, the force is only up. The resistance.
How is a horizontal?
Pushes back.
William, how does a horizontal force have to overcome a vertical force?
Because it's connected to it. It's also being affected
by
that force upwards.
William?
If it's physically attached to the Earth, then you're experiencing an upward force.
You're tying yourself in knots here. You're saying that a horizontal force affects a vertical force. Is that what you're saying?
Obviously.
How?
Because it's being affected by it.
How
If
is
you're
it being
standing on Earth, it's you feel your weight when you're connected to the Earth. So if you want to change that, if you want to reorientate that weight, then you need to constantly apply a force, constantly accelerate. In other words, to overcome the constant force of the Earth.
You're talking in such general vagueness. It just doesn't make any sense.
Okay, so we're going circle. We're just going in circles with this question. Do you have anything else to offer? Do you have anything else to offer?
Well, I'm trying to get from you. See, this is what I'm talking about. Your answers don't make sense. I can't understand
your questions and your answers don't make sense to me. Like,
well, can we ask how many people are watching right now? What do we got? 20 people?
I don't know about
33. We got 33. Can we get a vote? How many people understand what you explained about vertical forces affecting horizontal forces? Can people understand what you just said? Can we get comments? Hang on, let me check.
This is not the first time that this is brought up, so.
But your answers don't make sense, William. Like, I'm trying to understand them. Seriously, I am, but okay. I don't get it. How does a okay, I'm looking at the YouTube chat. Can people explain to me how a vertical force affects a horizontal force? Mr. Obvious. He says, yes, we understand. What is it? How does it work, Mr. Obvious?
It affects it because it's having to overcome that upwards push again to reorientate to
horizontal forces
to create a new vector.
Don't have to overcome vertical forces, William.
Okay.
El Capone. So, can you explain it to me, El Capone? Both have to be not touching the earth. What?
Again, I already told you, if it's in free fall, if it's not being affected by any other force, then a constant motion will create what you're asking for, in other words.
See, this is what I'm talking about, William. You need to get this idea clear in your head and write it out so we can all understand it, right?
Sure. I guess I'll maybe do that in the future. Just
yeah, I think it would really help us. Like, I'm trying to understand. I'm open to new ideas. Like, really, I am. Sure. I understand gravity as a theory, and I don't know what causes it. No one really does, but observations make sense with gravitational explanations, right?
Okay.
Yours isn't making sense to me.
You see, you have explanations to back up your observations to fit your presupposed model of a globe Earth, I assume. So again, that's not reality. Demonstrable reality shows that your observations are wrong of a downwards, an object moving down towards the Earth in free fall. Physics shows that is a misinterpretation of acceleration.
Okay. Can you elaborate on that, please? How does physics show that that's wrong? That's wrong.
Well, again, acceleration requires a force, and acceleration will always cause displacement. So if you're claiming acceleration in free fall, not only do you require a force, which is not there, you're also missing the displacement aspects.
Well, I explained why. I have explained why the water doesn't displace and move in the bottle when it's in free fall.
And your explanation was fantasy, which you admitted that that you would have to go into an imaginary, planet or outside reference frame to be able to demonstrate this. So, you admitted that.
The understanding that we have is that gravity affects all matter, and all objects accelerate at the same rate because of that. Now, when you drop a bottle, or when you push a bottle, sorry, not when you drop it, when you push a bottle, you're pushing the outside container. You're not pushing the water inside. So obviously the water wants to stay in place while the bottle around it moves until the bottle then comes into contact with the water and applies a physical force to the water.
That's the only way you can accelerate a vessel.
That explains. Okay, well, that's not the only way, because gravity.
It is.
Well, William, I gave you the example of magnetic forces being able to move a box of nails.
Only metal objects, but we're talking about liquids here as well, like water.
Yeah, well, like I said, if I can't escape the Earth's gravity to do a different gravitational experiment, then you're asking for something that's just not possible right now.
Exactly, because it doesn't exist.
Okay, William. Like I said, write a book, write a pamphlet, write something that puts your ideas in clarity for us all, and we'll all appreciate it, I'm sure.
Oh, yeah.
And no one in the chat's been able to explain it yet. So you guys are all watching and listening. Horizontal and vertical forces, how do they affect each other, guys? Why do we need to be off the ground in order for that skateboard experiment to work? Can someone explain that to me? And in fact, it doesn't even have to be a skateboard, William. William, you know what? It's even easier than that. It's actually easier than that. Do it in a car. Just drive down the road at a constant speed and put a scale vertically and put something in front of the scale and see if it's pushing against it. According to you, it should, right?
No, like I said, if there's a force already acting on that reference frame that you're accelerating, then you're going to have to overcome that force to create a new vector to be able to get the weight shifted to the back or to the vertical scale.
Well, William, how come I can make it work if I accelerate the car?
Because you're overcoming the constant force of the Earth. That's why.
How is accelerating a car overcoming the constant force of the Earth?
Because acceleration is increasing the force constantly.
Which force?
So
Which one?
The upwards push of the Earth.
You're saying
which you believe is
accelerate in a car. Hang on. If I accelerate in a car, I'm increasing the upwards force of the Earth?
No.
You just said that. That's what you said.
I did not say that. I did not say that. I said when you're accelerating a car, when you're accelerating a car, you have to constantly accelerate to overcome the constant upwards push of the Earth to be able to create a vector.
That doesn't make any sense. Hang on a second. Hang on. I got you here, mate.
Sure.
If we're in a car and we accelerate in a car, you feel a push from the back of the chair, right?
Yes.
That's because it's pushing you forwards. But according to you, that should also happen at constant speed, not just accelerated motion.
Oh my God, you're just going in circles now.
But that's your theory.
Going back to the
Earth
airplane
is moving up at a
experiment.
constant speed. You're saying the Earth is moving up at a constant speed. That's why we feel a force from below our feet. Why doesn't the same thing happen in a car?
Again, because the car's connected to the Earth and you have to overcome that constant force of the Earth.
Okay, so when I speed up in a car, is that overcoming that force, the gravitational force, the upwards force?
Accelerating a car, you're overcoming the upwards
what does
vector.
that statement, okay, William, what does
you're
that
creating a new vector when you constantly
mean?
accelerate. That you're creating a new vector when you constantly accelerate.
Why? And why doesn't it happen at
That's what force. That's what force creates. It's motion, which is a vector, a motion vector, which
William,
gives you your orientation and weight. That's why.
You're terribly confused about all this, and you've got gaps in your knowledge. I don't think you understand the science.
So, what in your model? What's the mechanism for buoyancy, and can you recreate it?
Are we going back to that again? Didn't we talk about buoyancy?
Yeah.
Buoyancy,
so can you recreate buoyancy by your alleged claim?
Listen, buoyancy requires gravity. If it's a stationary medium, right? It requires gravity. You can simulate buoyancy by accelerating an object, like a glass of water or a bottle of water. Accelerate.
That's the only way to do it. Is there any other way to recreate buoyancy?
William, why can't you simulate it by moving the bottle horizontally at a constant speed, which is what you're assuming the Earth is doing?
If it's connected to the Earth and you're at same principles, you have to overcome it. Let me ask, can you recreate buoyancy?
You haven't explained why being connected to the Earth affects anything when we're talking about horizontal motion. Horizontal motion is independent of vertical motion. Independent, right? It's independent.
Not when it's being affected by the vertical force. If you're going horizontal.
Okay, why? Why isn't it when it's being affected by the vertical? Tell us why.
Why is it
important that the vertical force is affecting it? How is it affecting it?
Well, if it's connected to the Earth, you feel a pressure. You can feel a force present.
But I'm talking about horizontally, not vertically.
Yeah, again, if you're feeling the upward pressure.
Does vertical force affect the horizontal motion?
How does a vertical
force affect horizontal motion?
Because it's there, it's constant.
Because it's there. That's not a satisfactory answer, William. Because it's there is not a scientifically acceptable answer. I can't understand that. No one can understand. You don't understand that. You're saying it, but you don't even, because it's there is not an answer. You have to accept.
Well, let me ask you this: is there a force present when you're connected to the Earth physically? When you're in contact with the Earth, is there a force present? Yes or no?
There are lots of forces, in fact. There's the earth pulling down on me. There's me pressing down on the earth. And then there's the reaction force of the earth pressing back up on me, which is supporting me and stopping me from falling down. So
Okay,
there's
so
three
there is.
forces for you.
So there's a force and a resistance to the force.
There are
Could we
three
agree on
forces.
that?
William, I just gave you, I can actually give you four. There are, but the three are the important ones. There's gravity pulling me down. There's me pushing down on the ground. Then there's the ground pushing back up.
So how
on
is
me.
you pushing down on the ground different from gravity pulling you down? If I may ask.
Because gravity is acting on all atoms that I'm made of, all matter that I am made of. But me pushing down is just the bottom of my feet pressing on a small area of ground, which is what we call pressure, right? Force divided by area. You heard that before? You know what pressure is?
So gravity's not making your body push down?
Yes, it is.
So it's the same thing. So that force
No.
is the same. So gravity pulling you down and you pushing down is the same force, is what you're saying.
No, William, no. Gravity pulling me down is the earth acting on me, and me pushing down is me acting on the earth.
So it's a chain reaction of gravity pushing you down.
No, it's different bodies acting on different bodies.
Exactly, it's a chain reaction. Without gravity, you don't have that downwards push, do you? So what you're saying?
Yeah, that's right.
Exactly. So it's a chain reaction of gravity. So it's just gravity pushing you down. That's what you're saying. And then the earth resisting that push, which just gives you your weight, right? That's what you're saying.
Yes, that's
exactly.
Right.
Yeah. So the opposite of that would be the earth pushing up and then inertia resisting that motion. So it's the same thing but opposite.
William, you're saying that the earth moving up at a constant speed is producing that force. And I'm saying it's not, because constant speeds do not produce force. Accelerations produce forces.
Okay.
You think it's constant speed. And that skateboard experiment would prove that, or doing it in a car would prove that. But you don't want to do that because you think that vertical forces affect horizontal forces, but you can't tell me how. It just does. You can't explain why.
But there's a force present, and you want to overcome that force or get a new vector different from that initial vector, then you're going to have to constantly accelerate. Yeah, it's pretty simple.
When you talk in generalities like that, no one understands what you're referring to. You have to be specific. Talk about the car, right? If in a car, we're moving at a constant speed down the highway with a bowling ball in the car, your theory suggests that something would have to be pushing that bowling ball to make it move with the car. Whereas I think it doesn't. I think inertia would cause it to keep moving with the car on its own.
So you're saying that that bowling ball would never stop, though, if it was just
as
to remove.
As long as there's no resistance forces on it, it would keep moving. That's
I
why.
agree, but on Earth there's always a resistance.
But you're saying that the bowling ball should slow down in the car and move to the back of the car. That's a good experiment for you to do, William. That's a good experiment because you think that objects tend to want to stop moving, right? So if you place a bowling ball on a fairly flat surface in a car and then drive that car at a constant speed, according to you, the bowling ball should move towards the back of the car because it wants to stop moving.
Again, you're talking. We're two different forces here. When you're
no, William. This is your general idea of inertia. Hang on, William. According to you, inertia is objects want to stop moving, right? Objects want to be at rest. That's your concept of inertia. That's your definition of inertia, in fact. So therefore, if we've got a flat surface in a car moving at a constant speed, and we place a tennis ball or a ping pong ball or a bowling ball on that surface, according to your idea, the ball should move towards the back of the car because it wants to stop moving. Whereas I think it would just sit there wherever you placed it.
Again, if it's at a constant
speed. On a train. Imagine you're on a train moving really quickly and you place a tennis ball on the floor of the train. According to you, it should move towards the back of the train because it should want to stop moving.
Again, you're having to overcome, if you wanted to do that, if you want to change the vector, then you're going to have to constantly accelerate. If it's moving at a constant, it's connected to the earth.
William, you're talking in generalities again. William, stop talking in vague generalities. Talk about the ball sitting on the ground in a train. Is it going to move towards the back of the train?
At a constant, it won't. But if you constantly
you said
accelerate,
it will, because inertia According to you, inertia is objects want to stop moving. And the ball is clearly moving with the train, right? So shouldn't the ball want to stop moving?
Yeah, but it's experiencing the upwards push, the upwards force of the earth. So,
William, you can't have it both ways. You can't tell me that inertia is objects wanting to stop moving, but then suddenly they magically will keep moving because there's an upwards force. The upwards won't affect the horizontal, William. The upwards force from the earth won't affect the horizontal. It has friction with the surface, fuckhead. Thanks, Exacerbate 200. Let's remove friction. Let's put a marble on a sheet of glass and try that and see what happens. And don't call me fuckhead because that's not very nice. I'm being very polite here. William, that's an experiment we can do. We can put a marble on a sheet of glass. And according to you, inertia makes the marble want to stop moving, so it should very quickly move towards the back of the train, right? Right, William? That's an easy experiment for you to do. Get on a train with a marble on a sheet of glass and see if it moves towards the back of the train.
All right, let me say hi to Del. Hey, what's up, Del?
How's it going, mate? Can you hear me all right, aye?
Yeah, we can hear you good.
Good.
So you want to chime in?
I've missed what's kind of been said. Obviously, I've just arrived here, so trying to gather where we're up with the discussion. All I can hear so far is this guy trying to steamroller you with some sort of intimidation tactics because he thinks he's some sort of huge intellect, and obviously he's an absolute moron.
All right, Del, I'm curious to see your explanation, to hear your explanations of all this.
Right, that's fine, but first of all, we need to agree on some first principles and get some grounding first, okay,
yes.
PK?
Yes.
So let's
what
talk.
is inertia, Del?
Well, what is inertia as far as you're concerned?
It's opposition to change in motion.
Right. So at the root of your worldview, if we remove matter, if we take air away and we take solid matter away, what do you think exists there?
What's that got to do with inertia? That's
because it comes down to some philosophical positions. Do you believe that at the base of reality it is a vacuum?
Holy crap! We're going from science into philosophy here.
Well, because it's based in listen. It's inertia is based in philosophy because the inertia model so far in mainstream physics is conceptual. Nobody has a full grasp, so it comes down to your worldview, okay, the foundations of where you start your reasoning. Do you believe at the base of reality, if we remove matter, there is a vacuum?
What's your definition of a vacuum? An absence of matter, yes?
So if matter was to be removed right now, what would exist?
Space.
What is space?
I'm not Albert Einstein, so I can't answer that.
So your worldview is a vacuum. Okay, so here's the problem, right? When we're talking about inertia, even if the Earth was to be shown to be moving in a linear fashion, right, and you believe that at the base of reality it was a vacuum, it would not matter how fast that reference frame moved it. You still would never create weight. You would never have any sort of resistance. You would never have pressure gradients or any of that stuff. So it's massively important because inertia is a very fundamental part of reality. Now, your worldview is a philosophical position of a vacuum, which is an absurdity. My worldview of an experienced being of practicality is that something precedes something else continuously. At no point in reality or my experience do I ever experience a void, a vacuum. So you, son, have a massive burden of proof because your reasoning and asking William the questions is based on your philosophical proposition of a vacuum at the basis of reality behind matter. So that's why you keep asking these daft fucking questions, sonny boy. So how can you justify to me that at the base of reality it's a vacuum? Justify it.
I don't need to, Del, because...
Yes, you do. Yes, you do.
Do you want to hear my answer or not? You're just going to talk over the top of me.
I want you to justify the belief that at the base of matter, it's a vacuum.
That question doesn't make any sense. You're saying the base of matter is a vacuum. A vacuum is the absence of matter. It's not the base of matter. It's the absence of matter.
So show me a vacuum, a perfect vacuum with nothing within it.
Are you for real? You want me to show you a vacuum? How am I supposed to show you a vacuum?
It's your belief, son. It's your worldview. So you can't justify it. That's not my problem. Don't turn it on to me.
Dill, are you in a room right now?
Yes.
If I was to evacuate all of the air from that room, what would be surrounding you?
I don't know.
You don't know. Really, you don't know. If I took all of the air out of that room, you don't know what would be surrounding you right now. Are you serious, Del?
Because I don't know what's at the basis, the foundations of reality. You believe that it's a vacuum. I don't know what it is. I don't believe it's nothing. I believe it's something.
What is it?
I don't know. It's part of the investigation. But this is the point. There's two positions that you can take. You can take the position that you believe in, which is at the base of reality, it's a vacuum, and then you can start your philosophical reasoning from there. I don't start from there. I just start from a progressive, practical process.
What you seem to have started from, Del, what you seem to have started from is I don't know. That's your fundamental position. I don't know. How can you build from an I don't know?
What I know is that matter resists motion. So in order for matter to resist motion, there has to be a cause of that.
Okay, Del, if matter resists motion, what would happen in my experiment? If we get on a train or on a plane and we take a sheet of glass and we place a marble right in the middle of a horizontally flat sheet of glass, which is moving with the train, Del, it's moving with the train.
Yes.
Shouldn't that marble want to move to the back of the train and stop moving?
PK, see if you keep speaking to me condescendingly, there's absolutely no need for that, sonny boy.
Okay, I'm sorry, Del. I'm sorry.
Weak here. Listen, the marble, I'm going to answer. The marble is already in the vehicle, traveling with the vehicle as you place it. So it's already moving at the speed of the vehicle and the sheet of glass. Now,
so you admit that it's moving. You admit that it's moving.
Yes.
Keep going. Yes, keep going.
Yes. So the marble's moving because it's attached to whatever's within that reference frame. Now it's moving at the speed of the reference frame when you place it on the sheet of glass. It's already moving at the same rate as the sheet of glass and the frame of reference that it's within. So do it so that the marble's out with that reference frame, and then try and drop it into the moving reference frame. What's going to happen?
Del, if that train. Listen, Del.
Answered, you fucko. Listen, fucko. You were answered, sunshine. You were fucking answered. Now you want to squirm. So do it in a different scenario. The reason the marble doesn't move is because it already has the momentum of the reference frame.
Which reference frame are you talking about?
The fucking train or the plane, whatever the fucking thing was.
Okay, Del, if I'm standing on the platform as the train goes past me and I look through the window, then the marble is moving, isn't it?
Yes.
In my reference frame, why doesn't it come to a stop?
Because it's attached to the reference frame with friction that's pressing against it. Do you know what friction
so there's so much friction. Is there so much friction between a marble and a sheet of glass? That's what you're telling me. There's so much friction, Del.
So listen,
because Del, you've just fucked up, mate. You've fucked up big time.
PK,
that's a totally stupid statement.
PK, see when you use the example of the train going past you as you stand on the platform. Now imagine you're holding the marble outside of the train and you let the marble go as the train passes. Does the marble go with the speed of the train?
Del, do you know what air resistance is?
PK.
Do you know what air resistance is?
PK.
You don't seem to know what air resistance is.
You don't answer fucking questions because you're a squirming lying sack of shite, son. No. The reason the marble is moving with the reference frame is because it was in the reference frame as it moved. Now, if the marble was sitting on the glass and the train was at rest and then the train accelerated to move, the marble will stay in its position. Will it not?
That's right, because it has inertia.
Yes. Inertia.
Because it has inertia. It wants to keep doing what it's doing. And if it's stationary, it wants to stay stationary. But if it's moving, it wants to keep moving, which is why it'll stay on the glass on the train. Del, it'll stay on the glass.
Right. So now you have to show me an example of a marble perpetually moving.
Exactly. That's what he's claiming.
What? Oh, easy. If I shoot a marble out into space,
you fucking wanker. You fucking wanker. If if I shoot a marble up the pink leprechaun's bumhole, it'll do magic stuffs. You fucking imbecile.
Okay, Dill, I suggest you write a book as well because your ideas clearly.
I suggest you stop reading fantasy novels, sonny boy, because your head's up your fucking ass, right? You don't even comprehend your philosophical position that you start from. You're an incompetent, illogical, irrational fuckwit, sonny boy. You're not here for honest discussion. You're here to try and intimidate William, and you fucking failed miserably because there's people smarter than you are, sonny boy.
Dill, let's go back to your question. If you drop a marble outside the window of the train.
PK, let's get back to your fucking foundation that you need to prove. Vacuums with objects moving indefinitely within vacuums. Prove it to me, son.
Okay, so you don't believe
No,
that
PK, show me a vacuum. Show me an object moving indefinitely in a vacuum. Go.
That's the claim.
Are you going to keep talking over me while I try to explain?
Are you going to justify your claim of nonsense, of vacuums and perpetual motion in a vacuum? That's your belief. That's what you're reasoning from and asking questions from. So in order for us to go further, you need to approve that premise first and foremost. Go for it. Until then, shut the fuck up and stop arguing from that premise. You don't have grounds to argue from it until you justify it. So we're waiting. If you keep talking from that position, we're going to keep ridiculing you. You need to prove a vacuum of perpetual motion or admit that it's impossible.
Okay. Are you going to keep talking over the top of me?
Are you going to admit that it's impossible?
So you're not. So this is your debating tactic, Bill. Your debating tactic is just to bulldoze your interlocutor, so you don't even give him a chance to answer because you know you can't actually answer correctly, so you're just going to bulldoze over the top of them. That's your tactic.
You've been answered correctly, sonny boy. Now, are you going to justify your position and admit that there's no such thing as a vacuum in perpetual motion, or demonstrate your position? No, one or the other, son. Before we move forward, we need a concession either way.
Okay. Do you know what a linear collider is, Del?
Are you going to produce a vacuum with perpetual motion, yes or no?
Yes. Yes, I am.
Where?
A linear collider. Do you know what a linear collider is?
Where is it?
Stanford University.
Can I access it?
If you perform the right task, you could probably access it, yes.
Where? Explain how it works.
Okay. A linear collider is a particle accelerator where a long straight tube is evacuated of all gas, so it's a complete vacuum, and electrons and protons are shot through it.
Sorry.
And those electrons and protons, Del, stay at the same speed. They don't slow down, Del. They don't slow down. So there's a vacuum and there's perpetual motion for you, Del.
Sorry. For two questions here, before we go any further.
How
long is the tube? And you made the claim that it's a perfect vacuum. Now, we cannot create perfect vacuums. That's a nonsense right off the bat. So don't make the claim again, son, because you're lying. Now, how long was the tube?
You don't even believe that vacuums exist. So how do you know you can't create a perfect vacuum?
It's impossible to create a perfect vacuum, you absolute cretin.
I think that's a pretty general fact there, yeah. That vacuums don't exist. Perfect vacuums don't exist.
This guy's not an engineer. He doesn't have a clue what he's talking about, right? He's a clown. So perfect vacuums don't exist, sunshine, right? So that's a lie right away. Now, how long was this tube?
Okay, so I actually know that perfect vacuums don't exist, but they can get down to a level where the amount of matter is negligible and irrelevant to the motion.
Nonsense.
So they can actually do that. Nonsense, really? That's
how
nonsense.
long is the tube? Answer the fucking question, son.
Let me look it up.
Yeah, I'm going to get my tobacco while you faff about reading your fucking fairy tales. I'll be back in a second.
3.2 kilometers, Del. It's 3.2 kilometers. There you go.
All right. Well, I guess we'll wait a bit. So
why is Del so aggressive, William? I don't understand why he has to be like this. Is a tactic of the exhausted mind. When someone is so verbally aggressive, it's someone who's run out of ideas, typically, right? Is Del usually this aggressive, or is he just not able to argue in a sensible, coherent way?
Yeah, well, usually when people can back up practically what they claim, and they just continue, then it has to be called out, and I guess showing a little
Yeah,
bit of
but he's
passion
doing more
towards
than
that.
calling it out. Dell is overly
This is demonstrable
aggressive
reality.
and
You should be able to
insulting.
demonstrate your claims.
Listen, PK, I listened to you trying to intimidate William and belittle
I'm
William
not
before.
trying to intimidate anyone,
Listen,
Dell.
fucko.
I'm trying to
You
get
don't
answers.
listen. We
I'm
weakling.
trying to
You
get
don't
answers, Dell,
listen,
and you
weak
can't
man.
even provide answers. All you seem to be able to do is bulldoze over the top of people,
listen,
throw
weakling.
insults around, and not be able to justify and listen to answers to your questions. So
Listen.
you throw questions out there,
Listen.
you don't give an opportunity for an answer, and this is your debating tactic. Or we're not really debating; we're just having a discussion. But because you can't accept and have a credible discussion, you just want to bulldoze and barrage over the top of people.
Right, is that you finished with your virtue signal of your victimhood? Are you done? Weakling.
That'll do for now.
Listen, weak man. See, when you try and intimidate people, I don't suffer fucking bullies. You didn't speak to William with respect. You spoke to him with a belittling, condescending manner. You fucking intimidating, bullying little fuckstick. So I don't suffer bullies, and I'm going to treat you like the weak little spineless fuck that you are until you fucking apologise and correct yourself and start walking with fucking manners and respect. Until then, you're a fucking piece of shit in my shoe, and I'll speak to you like that until you fucking show me otherwise. Fucko. All right?
Okay. Thanks, Dell. William, did you feel insulted by my approach there? Did I bully you, William? Were you being bullied?
You're definitely being condescending.
Well, William, you couldn't answer my basic questions, and your argument has so many logical holes in it. I'm trying to understand it, and
let's try and understand then. Let's go right back.
But Dell, if we start with your position, which is I don't know, that's your basic fundamental first principle position. I don't know. Well, there's not really a hell of a lot we can build from that, is there, Dell? Here's my position. Here's my position, Dell. The science that I'm describing and that conventional science that we all know made the world around you, Dell. Every bit of technology that you use, every time you get on a plane, every time you get in a car, it relies on technology.
Shite yet again. I'm not listening to you. So shut the fuck up, wee man, because practical engineers built the world around us. No, you fucking scientific fairy tales. Right?
Listen, Dell, you're the one that always wants these magical experiments.
Listen.
And I'm telling you, the experiments are all around you. Your everyday life is full of technologies that builds upon the science that we all know.
Here we go.
Science hasn't built shit. Hasn't built anything. So you tell me which of those sciences is more credible. You're one that hasn't built anything, or my science that's built the whole world around you and allows us to talk from different parts of the world right now.
Right. Yeah, this has been on for a bit.
Because all that's happening now is we're getting an emotional barrage of some fucking threatening, trying to fucking argue and slander our characters, right? Because he's irrational and he's incapable of actual, practical discussion. So are you finished with your emotional outbursts yet, Sonny boy?
Am I muted or not?
Yeah, you're good. You're good now.
Are you finished?
Okay, go ahead, Dill. Enlighten us all. Go.
Are you finished? Are you going to keep
enlighten us? Go.
Stop interrupting, you ignorant wee fan.
Tell us how you don't know, and then build from that. Go ahead.
There's no discussion with this, correct? And he's totally irrational. How can you have any kind of...
Come on, Dill. Tell us how you don't know, and then build on that as your first principle. Go ahead. Go.
Well, the fact of the matter is that no human being knows what the foundation of reality is. No human being knows what's at the root of reality. That's why it's all up there for investigation. People like this guy are religious in their nature because they think they've got answers out of vacuums. They make statements of perpetual motion within places like a vacuum that do not exist to human beings. No human being has access to a perfect vacuum. No human being has ever experienced perpetual motion in the entirety of our existence. This guy thinks that he's got the right to postulate such a position and then make lying statements that engineering is founded upon these philosophical premises. The fact of the matter is that engineering operates on the observed phenomena and how things actually behave. This guy's got the religious aspect of the worldview where it goes to the root of reality and starts creating creation stories of what creates matter and is at the basis of reality. He's a fantasist, an absolute lunatic who doesn't even comprehend the worldview that he espouses. So the reality for me is that We can observe phenomena, we can observe things like inertia, and then we can ask the questions, what gives rise to matter? What's actually at the base of reality? Which people are trying to investigate, including the nonsense of the Hadron Colliders and these things. That's what they're actually looking for. This guy doesn't comprehend any of that, though. He thinks the answers are there. You know, even if he goes to his chat GTP and talks to it about inertia, it will admit and concede that it's a conceptual notion of inertia. And the mainstream model actually espouses that inertia is something intrinsic to the matter. So, you know, this guy doesn't even comprehend the worldview that he's trying to operate from. So once you're ready to be honest and admit that you come from a philosophical position and, you know, admit that, then any discussion afterwards is we're just going to talk past each other because you won't concede that your worldview is faulty. So until you can produce a perfect vacuum and show perpetual motion for a prolonged period of time within a vacuum, then you don't have a grounds to argue from there. And unless you admit that, you're just being totally dishonest.
Okay, you done? You done, Del? Okay, I actually do want to agree with part of what you said there. I actually agree that we don't know anything as fact. Absolutely. Science is a process of constant refinement. And the philosophy of science is that nothing is proven ever true, but can be disproven. I attempted to disprove some of the ideas that William puts forward. And with a couple of simple experiments, because this is William's basis. William's whole shtick is using simple experiments. So I wanted to come up with a couple and see how they correlate with William's ideas, like the skateboard experiment. Del, can you poke a hole in my skateboard experiment, please? How does a vertical force affect a horizontal force?
Because it's always present. It's pushing upwards. If I'm pushing you in a particular direction, yes, and something else pushes you in a perpendicular direction, you're going to go off in a diagonal.
That's right. That's what I explained to William. Right. But if you're moving horizontally at 10 meters per second and a force is pushing you from 90 degrees to that, is that going to stop you moving horizontally at 10 meters per second?
The friction of the ground is going to be there.
Ignoring resistance, Del, obviously. Ignoring air resistance or any other friction.
Well,
is it going to affect your horizontal velocity?
Is your velocity, is it constantly being powered?
Let's assume it's a frictionless environment.
No, we don't live in a vacuum, son. There you go again, trying to espouse vacuums.
Oh, man. Del, we have to operate with some fundamental assumptions here in order to simplify things, right?
Yes.
So
I don't believe in vacuums. I don't believe in vacuums.
Assuming a ball is rolling across the floor at 10 meters per second, it will maintain that speed more or less, right? More or less.
No. Unless it's got a power source behind it constantly pushing it at 10 meters per second.
Okay. I'll concede that point. Let's say we've got a toy car with a battery powered motor, and the car is moving along at 10 meters per second. Let's make it 1 meter per second, Del. A battery powered car, right? It can maintain a constant horizontal speed across the room. Let's say north to south of 1 meter per second. Now, if you blow it from the west with a wind or apply some other force to it, that's from the west only, is that going to affect its north-south velocity?
What, with a wind? If the wind's strong enough, then of course. Listen, just stop a wee second, right? Because the fact of the matter is any example you give of a car, whether you push it and let it lose its own momentum or you put an engine on it and it continuously moves, the ground is going to continue to push upon it.
So you're not going to answer the question?
If I drive my car at 100 miles per hour along the motorway, I'm doing 100 miles per hour and I have an engine in there that's giving me the constant power of push to keep doing 100 miles per hour. But guess what? The ground's still pushing up on the tyres. I'm still in contact with the ground. So as I drive at 100 miles per hour, the tyres are still being squashed because there's a compression.
Let me give you another example, Del. Let me give you another example. Yo,
The airplane
yo,
one
let's
now.
let's fly a plane, towards north. Let's go northwards in a plane, and let's say there's a crosswind towards the east. Is the crosswind going to affect the northward speed?
Yes.
Bullshit, Del. That's wrong.
Have you ever seen listen, I live right next to
Del,
the
Del,
listen,
you've just failed
PK,
7th grade
PK,
science. You've just failed 7th.
Just mute
Okay.
him, William. Just mute
Yeah,
him.
just-
He
no,
doesn't
yeah.
have the answer. He
Yeah,
doesn't
yeah.
have the answer. So when an
Yeah.
aircraft, everybody can observe this when it's coming into land and there's a crosswind, it fucking gets blown about fucking side to side. I mean, is this guy's a retard? This guy is literally retarded. He doesn't think that a crosswind affects an aircraft. What a fucking moron.
No, yeah.
Does it affect its north-south velocity?
Yes, it gets blown to the left or the right, whatever way the crosswind is going.
But does it still move north at whatever speed it started?
It has the power of the engine given it the velocity. It's still going to be blown off its track. It doesn't go in a perfect straight line. If a wind blows, it gets blown off of its course. Are you demented, son?
Del, I think you're clutching at straws here, and you're searching for technicalities to try and throw off the general principle here.
Let's PK. Let's go to other examples. Let's go to vertical examples, okay? Not horizontal examples which oppose.
Vertical is
the
different because vertical's accelerating.
Sorry?
Vertical is different to my example because vertical accelerates due to gravity.
No, it doesn't. There's no downwards acceleration.
But you still agree that the rate of approach between the Earth and a falling object is accelerating motion, though, right?
Visually, there's a change, and visually there's an acceleration.
So you're saying that if you jump out of an aircraft, Del, you don't speed up towards the ground? Or the ground doesn't speed up towards you?
PK, see when we're giving answers and responses, don't just butt answer and actually try and have
Give me a question. Give me a question, Del. Give me a question.
No. When we drop an object or you jump out of an aircraft and there's an observer, optically there's a change. Now that can be interpreted in various ways. However, if the skydiver has an accelerometer attached to
Are
it,
you serious, Del? Are you saying we
Yeah,
can't
this is
measure?
PK.
just mute
Yeah,
this.
I'm gonna mute him again.
Yeah.
You want to give your example? Yeah.
Yes, if we jump out of an aircraft with an accelerometer attached to us, that accelerometer reads zilch. Now, even an accelerometer, if you launch it, as soon as it leaves your hand, that being that the force is no longer attached to that accelerometer, instantaneously registers zero. When you jump out of an aircraft, that's what happens. And you can change your body shape all you like, and it can be perceived from the ground that you're now accelerating down. However, that accelerometer that detects acceleration detects no such acceleration in that vector. The other examples that William's done, I have done, Andrew's done, anybody can do. A basic accelerometer of actual downwards acceleration shows a displacement of gas, liquids, and solids under conditions of actual acceleration. Now, when we let that object go into freefall, we witness none of those things occurring. So, PK, there is no physical downwards acceleration. The only thing you're going to do now is squirm. Go for it.
Okay, Del, let me pose a scenario for you. Very simple scenario. And please don't talk to me about air resistance and all the rest of it. If I stand on the top of a 100-story building, right? So I'm on the top of the World Trade Center, as it used to be, and I drop a marble. And if a marble takes 1 second to drop from the 99th to the 98th floor, will it still take 1 second to drop from the second to the first floor?
Depends, are you interpreting it optically or are you actually physically?
Oh my God, Del, seriously? That's your answer? That's your answer?
It's not an
PK,
answer.
can you see the screen?
I can't
PK,
believe
can you
it,
see the
Del.
screen?
Hang on. I need a cough lolly because this is too much. Hang on a second.
You're the fucking cock wally, you wee wanker.
Hang on. Del,
It wasn't an answer. Listen, Danny, you're just
Del,
you're just no smart. Listen, son. Listen,
insulted you.
you're an idiot. You're a fucking incompetent, illogical, irrational weakling. You're no smart enough to engage me, fanny wank. Right? Now, when I try and answer you, you take what the first thing I say is my answer. When I'm trying to understand your position, because you can't clarify your position because you're a religious liar, right? So you
Go ahead,
squirm.
Del. Answer the question. Answer the question. Falling marble of a building. Answer the question.
It's your claim that it accelerates. It's not my claim.
My claim is that the time it takes to go from the 98th to the 97th floor will be a lot more than the time it takes to go from the second floor to the first floor. That's my claim.
Okay.
Are you refuting that claim?
Nope.
Well, you just said that things don't accelerate.
Yes, because
that's acceleration, isn't it?
Yes, acceleration is a change. I already said that. If you clean your ears out, we observe a change, which is an acceleration. Okay. Now the problem is that your claim is that the object is moving in a particular vector. Okay. My claim is not that it's moving in a downwards vector. That's your stick. So, fucko, when we show an example of an accelerometer which is claimed to be moving in a particular vector, it does not register said acceleration in that vector. So it's not moving in that vector. There is a change that happens. We all can observe the change that happens. The problem comes is when people that you claim that the change is due to the object accelerating in a particular vector. Now that's the point of contention. Do you comprehend so far, PK?
Is the ball accelerating down or is the Earth accelerating up?
The ball is moving still upwards, losing the momentum that it had at the rate of the reference frame. It's still moving in the same direction.
Is its velocity changing?
Yes.
Therefore, it is accelerating.
Yeah, listen, I just said that to you. Obviously, you don't comprehend. A change is acceleration.
A change in velocity, not displacement, velocity.
Any change is an acceleration, you weirdo.
No, it isn't.
Wow. Emotions are changed. So if something's at rest and something changes, it has to begin moving, ergo an acceleration. You are retarded.
Del, Google the definition of acceleration for me, will you please?
I don't need to Google it. I understand. I'm a mechanic. Change.
You're a
science.
mechanic?
Listen, the basis of science. PK, just listen. What's the definition of acceleration? Change.
Changing what? Changing your clothes? Changing your bedroom? Changing what?
Any motion.
Changing motion.
Yes.
Really? So
listen, PK, science, the basis of any science, any observation is change. Now, understand the word change. Change is motion because something has to move in order for us to observe the change. So if it's at rest and it changes, it means it moved. Ergo, an acceleration.
Okay.
Do you
do you believe that things can speed up and slow down?
Yes.
What's the one word that describes those motions?
What do you mean? What's the word that the change?
If something speeds up, what's it doing?
Accelerating.
There you go. You just defined it. Changing speed. Changing speed. Not changing motion. Not changing position.
PK. Change. The word is change. Yes, you get it.
Changing position, though? You think changing position is acceleration?
Any change is an acceleration.
Changing position?
Did it move?
How did it move, though? Did it move?
It doesn't matter. If something changes, there has to be motion.
Okay. Del, if something moves...
Wow. This guy is a fucking... he's like Flatzoid.
Yeah.
This is like Flatzoid.
Del, if a car is moving at 50 kilometers an hour at a constant speed, is it accelerating?
If it's a constant velocity.
It's a constant.
Yes.
Here, PK, let me just address.
If it's changing, it's motion. If it's changing, it's motion. From one place to another.
Address PK real quick. Let me address your free fall, the change in velocity and free fall. So the change in velocity that we experience, the increase in change in velocity of a free falling object and the Earth, is the loss of momentum per second that increases the higher you drop it. The higher you drop an object, the more time it has to decelerate. So the higher the difference in speed is going to be between the free falling object and the Earth. That's the acceleration we visually
your claim
see.
Is that there's some medium that causes this change in momentum, right?
Inertia.
No, inertia is not the medium. Inertia is just resistance to change in motion. What's
so inertia?
What gives the body? What gives it? Listen, this is where it needs to be clarified. If I grant you, PK, that it's a vacuum, right? What is inertia in your worldview then?
A resistance to change in motion.
So what resists? What is causing the resistance?
The fundamental property of matter.
So what is that? So are you claiming inertia is inherently in the matter?
Yes, objects want to keep doing whatever they're doing.
So if you claim inertia is a property of the matter, is that correct?
Yes, that's
Isolate it and show me inertia within matter.
It doesn't work that way, Del. Like,
if I claim, listen, PK, if I claim
I'm supposed to pull inertia out of an object.
If I claim matter has some property in it, I should be able to isolate it and show you that property. Now, you've just made the claim that matter has a property within it called inertia, so extract inertia from the matter and isolate it and show me it.
Well, that's like asking me to extract mass out of matter. You have to agree that matter has mass, true? You have mass. How would you extract the mass to show me that mass?
No, mass is a mathematical description of matter.
So it's not a property of matter?
No.
So you don't have mass?
You can call it whatever you like. All I have is matter, right? You're the one with the conceptual notions. So don't try and wriggle. You've made the affirmed statement that matter has inertia within it. Now you have to justify that by isolating this inertia stuff and showing me what it is. Because as far as I'm concerned, the only way matter moves or slows down is because it's acted upon externally. I don't believe that matter has some magical stuff in it. That's your Harry Potter gibberish, son. So until you can justify a few things, vacuums, perpetual motion, and that matter has an inherent property in it called inertia, you're talking shite, son. So can you isolate inertia from your matter?
Okay.
No, you can't. Wriggle and squirm.
Del, why does ballistics work? Why does the science of ballistics work? How can we shoot a cannon 25 kilometers and get it to land exactly where we want it?
But through practical practice. It's got nothing to do with conceptual notions of inertia.
Really? You don't think that we understand this to the point where we can calculate the exact escape velocity and angle we need in order for an object to land exactly where we want it?
PK, you can calculate the trajectory of an object based on practical reference. It's the practical that came before the mathematical description. Now, the problem is that you're making the affirmed statement that matter has a property in it that you call inertia. Now, I've already told you, even if you go to your chat GPT and hold it to account, it will admit and concede that it's a concept. All we have is matter in motion, and we have concepts to explain it. Now,
okay, we're back to this argument again. Yes, I agree. Science is not what we know for sure. It's our best description of what we understand, and it's constantly being refined. It's the philosophy of science. Okay, we've gone in circles here.
So now that we've established that, you cannot keep making the statement that matter has a thing within it called inertia. If matter is resisting some sort of change, it's because of an external factor, not because of the matter itself. Matter does not move on its own and does not slow down on its own. That's preposterous.
Okay, it doesn't slow down on its own because it needs a force, because slowing down is change in velocity. But if you start an object moving, it will want to keep moving, and it will keep moving unless there's an opposing force on it.
Again, you're going back to these vacuums and
yes. Show me
perpetual motion.
Show me an object moving perpetually. You can't.
Okay. If we have a almost frictionless surface, Del, why do objects tend to keep moving on those surfaces?
Show me perpetual motion.
Listen, Del, an ice skating rink. If I push something along on an ice skating rink, it will tend to want to keep moving.
And it will slow down. And it will slow forever.
Hang on, Del. What's slowing it down, though?
Listen, PK, stop trying to reverse the burden, son. You keep making statements of perpetual motion. You've been asked for examples, and you keep giving us examples where there is no perpetual motion. So why do you keep espousing perpetual motion?
Okay, because it's impossible to have a perpetual motion machine. That's why.
Exactly.
Exactly, yeah.
Do you know why, though?
Because matter doesn't move perpetually.
No, that's not the answer, Del. It's thermodynamics. That's not the answer. It's because you cannot eliminate all friction.
Right, because you don't know what the cause of inertia truly is. That's why you cannot remove inertia.
Okay, fine. What are we exactly arguing about? Let's go back to my question with dropping a ball off a building. Don't you agree that it changes its speed as it falls?
Yes, there's a change. We all observe a change
in speed. You observe it, but it's an actual change, though, right, Del?
Well, yes, there's a change. Yes.
But you say it's just what we observe. Is it what we observe, or is it actually speeding up as it drops?
There's an increase in velocity between the free falling object and the Earth. There is an increase in velocity. I agree, but it's not because the object is accelerating down towards the Earth. It's because it's decelerating. Therefore, the difference in speed between the free falling object and the Earth is increasing. That's because the Earth is remaining its constant.
I get that. What is causing that decrease, though? What's causing it?
This is us getting to the root of it now, right? So as Williams just explained to you, we totally agree that there's a change. This is the problem, PK. Your worldview claims that it's the object accelerating down. Yes. Now, a rate of that sort of acceleration with any accelerometer and any vector, we can attest and witness that what happens through the displacement. Now, in your worldview, you're claiming the massive acceleration without the displacement. So you have to justify that now. You need to show me.
I did justify that. I did explain why that happens.
No, you didn't.
Yes, I did.
If you had an explanation,
if I take William's bottle, which is half full of water, and I drop that bottle, the water which is at the bottom of the bottle will stay in the bottom of the bottle as it falls.
Right.
And the reason for that is because the gravitational force is acting on all of the matter, the bottle plus the water molecules at the same time, accelerating them all at the same rate. That's why they stay in the same position.
PK, can you see my screen?
Yes.
Okay, so the one on the left here, that one I actually accelerated down. And
I know. It's attached to an elastic band or something, right?
Exactly. So why isn't this displacement happening on the right when it's in free fall? You're saying because everything's
on the left, because on the right, it's accelerating down at 9.8 meters per second squared, because that's the gravitational force acting on it alone. Whereas on the left, you're adding an acceleration to it with the elastic. You're causing it to fall at a greater rate, or accelerate, at a greater rate than 9.8. So it's the same as pulling it upwards or pulling it sideways. You're pulling it down faster than its natural rate of acceleration due to gravity. That's why.
But when I accelerate, because 9.8 meters per second is 32 feet per second. When I accelerate 1/8 of that speed in any other vector, in other words, 4 feet per second in any other vector, I'm gonna get this displacement. Why is it that I have to accelerate 8 times faster than that in free fall?
Because gravity works on the vertical vector, William. When you're talking about accelerating at a different rate, you're talking about horizontal acceleration. Where gravity
any other vector. It could be.
Here's the thing. It's this guy's claim that there's such a force that can accelerate gas, liquids, and solids simultaneously. Now, other than circular reasoning based on a faulty interpretation, you have to qualify how a force would act like that. So show us it in some other vector.
Exactly.
Gravity works mass between mass. So how can I show it in another vector?
Well, it's just your belief system then, mate. It's just circular reasoning. You cannot qualify it. We can qualify your position in any vector.
Okay. Let me show you. Okay, I'll give you an example of it. I'll give you an example. Have you got a telescope? If you get a telescope and you go out at night and you observe Jupiter, you will see moons orbiting Jupiter. Now, what do you suppose is holding them in that circular orbit?
Doesn't matter, PK. You're
doesn't matter. Hang on. Did you say it doesn't matter, Del? Guess what, Del? It's gravity. It's gravity that holds those moons around Jupiter. It's gravity holding our moon around our planet. It's gravity holding us around the sun. There's lots of examples for you, Del.
Yes, PK, we know your mathematical, your religious science son. However, we're talking about the real world and practicality.
That is the real world, Del. You can observe it yourself.
Listen, PK, I can look outside and observe parallel lines converging in the distance. Does that mean that that's what's happening?
That's perspective, Del. That's just perspective.
But that's how it appears to me.
Well, how do you explain balls going around a planet through your telescope lens.
All you're doing is having an optical observation. It's got nothing to do with the physics of our realm here.
So you're suggesting that some entity is creating a light show in the sky artificially that matches an explanation of orbiting planets. That's what you're saying.
Why are you using every fallacy in the book and straw manning and putting words in people's mouths? Are you that weak in your position, son? Here, let's get back. Listen, just mute the prick. Fuck him. Listen, fuckle. We're talking about physics of reality here. So you claim there's a force that can accelerate gas, liquids, and solids in lockstep, although we're showing you what actual downward acceleration looks like. You're making the claim, it's because you're going faster than 9.8 meters per second, blah, blah, blah. Any acceleration of 9.8 meters per second shows massive displacement of gas, liquids, and solids in any vector, son. So you're using circular reasoning, trying to wriggle your way out of it by jumping to some optical observation of fucking Narnia, right? You make the claim there's a force that can act on matter simultaneously, accelerating them all in lockstep. Shows it. Don't use circular reasoning. Use some other vector to justify your position.
Del, why is it always 9.8?
What's 9.8?
The rate at which an object reaches the Earth.
Is it? So if I've got a test tube of 2 meters long and I drop a ball bearing in there with a fluid in it, is it your claim that ball bearing accelerates through the fluid?
No.
What happens?
The acceleration is counteracted by resistance forces of the fluid.
Right. So in the example that William's shown you of the accelerometer, you claim that the water, the gas, and the bottle all accelerate together downwards, correct?
Yes.
Justify it. Show me it in another vector.
Holy crap.
Listen, if you're going to claim a force that can do certain things, that means that you should have access to that force and that you can demonstrate the force regardless of any conditions. The fact of the matter is all you have is circular reasoning based on a presupposition of the Earth being a sphere. Then you drop an object and you make an optical interpretation of what you suppose is going on, right? Now, nobody denies a change happens. What's in question is a claim of a force acting that can accelerate gas, liquids, and solids simultaneously. Now, human beings, factually, 100% fact, do not have access to forces like that, because in every example, which is the premise of why an accelerometer works, that we witness a displacement when force is applied. In order for your force to work, it would have to be applying various force to the gas, the liquid, and the solid simultaneously.
Yes, it does, Dill. It does.
No, show me it.
Well, William shows you in his videos, when he drops the bottle, all the matter falls at the same rate. There you go.
Other than Freefall.
Other than
It showed you in Freefall.
Other than Freefall, though.
So there's your special pleading. Now, in order to qualify it and it's not be a special plead based on your circular reasoning, show me it in another vector.
How am I supposed to recreate gravity in another vector?
It's not my problem.
Okay, how about this? Have you heard of the experiment, I forget what it's called, where you take two very dense balls and they move towards each other over a period of time?
Does it show non-displacement of gas, liquids, and solids being accelerated?
It shows solids being accelerated.
Does it? But the claim is gas, liquids, and solids are being accelerated in unison with each other. Does your test match that claim?
Yes, if I put a glass of water inside that ball, then the gas, solid, and liquid will all accelerate at the same rate.
At 9.8 meters per second?
No, because I would need an Earth to do that.
All right, so you've got an excuse. Okay, so now we're getting
Okay, Bill, thank you. Yes, because I can't create another planet Earth, I can't do the experiment for you. I'll concede that point. Thank you very much.
Well, listen, the flying spaghetti monster is real, and because I can't create the flying spaghetti monster doesn't mean that it's not real.
Okay, Dill.
Nice.
Asking me to perform impossible tasks is not a win. It's not the victory you think it is, I'm afraid. Listen, Dill, what kind of mechanic are you? What kind of mechanic?
You're the one making these impossible claims.
Exactly, William. You're making impossible claims and trying to shut on to us.
What kind of mechanic are you?
It doesn't matter, son.
It doesn't matter. Okay. Do you use measuring devices, Dill? Do you use torque wrenches?
I'm not talking about me. I'm talking about your claims, Sonny
Do
boy.
you know what a torque wrench is, Del?
Can you show me a force acting on matter, accelerating it all simultaneously in lockstep without using circular reasoning on the vertical based on your presuppositional interpretation? Show me another vector of that acceleration.
Del, if I could take you onto another planet so we could do that experiment.
All right.
You lose.
Right, so,
you lose.
Okay, thanks.
All right, so muting you real quick. So I'm just gonna go. I guess we could do our closing statements. I guess if you have any last words, PK, now will be the time because I'm gonna be wrapping it up already pretty soon. So go ahead if you have any last thoughts or questions.
Even with all the insults which are masking your inability to answer my questions, I still thank you for your input there. William, I have one thing to say to you. One thing. Put your ideas on paper so we can all scrutinize them properly. That's all.
All right.
Del, you can help him. You can do it as well, Del. Both of you. You can co-author a booklet of your ideas and theory. Okay.
Well, what you can do is
add it to the library with all the books that match my ideas. Okay. And then they can be scrutinized.
We don't live in fantasy idea world. That's
your first page can say, "I don't know," and you can build from that. I don't know.
Or I can appeal to
fucking moron.
Or I can appeal to non-demonstrable physics that exists in Harry Potter Narnia land like you do, son, and just fucking circular reason my way through and dirt my way through anything by just making outlandish claims and then saying, I need another planetoid, I need to leave the Earth reference frame in order to demonstrate my Narnia claims. In order for me to show you Narnia physics, I need to go to Narnia, which we don't have access to, but it's real, and you better just believe me.
Yeah. So it's funny how he tries to mock the fact that we don't know what causes inertia, right? And which he concedes to actually admitting that we don't know, but yet he tries to mock that we don't know, even though he conceded that he doesn't know. He's a complete fucking idiot. Like
that's the thing, William. We're the ones that are displaying that intellectual honesty, and we're in a process of actually trying to comprehend. Now, we're not making any definite statements. As far as we're observing the vectors upwards, as far as we're observing, we have a constant weight, which, denotes a constant. Whether that's, two factors at play, we're asking these questions. A big question is for me and obviously yourself is, what is inertia? And again, as I explained to that guy, PK, even if you go to, I've got a recorded conversation where ChatGPT actually had to concede that, when I asked it what inertia was, it came back straight away, inertia is a property, like he said, of the matter. I put it to ChatGPT that's nonsense. And how can you extract inertia from matter? Can you isolate it? It came back and admitted, no, you're correct. Obviously, we just use that as a conceptual explanation of how matter is behaving, but we really don't know. So that's the mainstream model, and anybody that's honest within that model would concede that. But guys like PK are no honest, and they want to shift it onto us because we say we don't know, like that's somehow a negative. Well, if you're in a practical process of comprehending something, then of course you have to have the attitude of you don't know. I'm not religious, you're not religious. We don't just make up Narnia stories like PK and then project, that to the observation and try and interpret to fit that bias. That's not how we operate. I've simply just taken claims that these people have made and then put it to the test. So vacuums, perpetual motion, can't show you my example unless I'm in some other reference frame away from Earth. I mean, that's not an honest intellectual process to be through. That's just a religious bias. It's ridiculous.
No, yes, definitely. Especially if we can demonstrate that even in a vacuum, if you put a platform under your feet and you accelerate up at a constant, your weight's going to increase.
Yes.
So showing that there is a resistance to motion, even when there is no air resistance.
Exactly.
So again, just because we don't know the cause, that doesn't mean it's not there. It's clearly there,
Exactly.
Demonstrate that.
If they took their little chambers that they're talking about and we had a fucking, a mile-long tube up the way, as you say, William, and you placed a little lead weight in there on a scale and then fired it straight up, you're going to get an increase in the weight because the matter's going to resist. Regardless of how good you think your vacuum is, the inertia is still going to be present. These people don't comprehend that even if it was we did have a true vacuum at the base of reality, the reference frame could be accelerating at any rate at once. You still would never create any weight. The matter would just equalize to the speed that the reference frame is going at indefinitely. You would never create a pressure gradient, a density gradient. It wouldn't work because matter has inertia. There's a factor that's been overlooked. The mainstream model says it's in the matter, which is just the same as Flatzoid saying that matter can move itself. So we know matter cannot move itself. We know matter cannot slow down itself. But these people at PK want to say, well, no, matter has to have an external force to make it move, but it has its own thing called inertia, which slows it down. That's preposterous.
No, yeah. You can clearly see that they're just basically saying the same thing, but, just instead of, like you said, instead of moving itself, it stops itself.
Yep.
But yeah, the resistance and the cause of motion are both external. They have to be because matter is inanimate, like you say. Like we can all test matter. It doesn't move on its own, doesn't react on its own. It requires a cause.
Exactly. And again, that this notion that matter somehow exists independently and within a void, a vacuum. I mean, it's totally fucking nonsensical. How a human being can reason to that is beyond me, because as a human being, the only practical reasoning that you can draw upon is that something precedes something else. There is no point in reality where no thing precedes something. It's preposterous. And nobody has grounds to reason from there as far as I'm concerned, unless they can justify it.
Yeah. I mean, he literally displayed that he's just religious. He, like Matt says here in this comment, he prefers explanations over demonstrable physics. Can't make it up. He literally said there's hundreds of books that, with explanations and explanations here and explanations there. But I have demonstrations. I have practicality. I don't need explanations in a book, So he was just displaying how he's just a religious zealot and just believes everything he reads, and he prefers explanations over reality.
And he would be the first person, if a religious person came along and says, I've got a book that explains my existence, my religious book, he would be the first person to say, that's just a religious book, it's just text. Right? But he's doing the same. He has a religious text of explanation. Exactly.
No, yeah. At the end of the day, you can't really reason with people like that. People that are, just stuck in their beliefs, and not willing to be honest with themselves to engage, in a discussion about objective reality. If you just have explanations and beliefs and theories, and then you have the demonstrations that back up those beliefs, and then they ignore these demonstrations, then there is no conversation there. At the end of the day, it went nowhere. Obviously he was already set in his mindset, just like any other religious person, and they're not going to change their mind, regardless of what reality is showing.
I mean, accelerative force, being able to accelerate matter simultaneously doesn't exist. Nobody has access to anything like that. It's absolutely ridiculous. And then the excuses that you get, well, in order for me to demonstrate it, I need to leave the Earth reference frame. That is absolutely incredible. For somebody to claim they're rational, logical, scientific to make such a statement beggars belief, as far as I'm concerned. How you can claim to be any sort of reasoned person, looking for an excuse to escape the reference frame in order to justify your Narnia physics. Narnia physics exists in Narnia, which we don't have access to, but we have to accept it because they're transposing Narnia physics onto their interpretation of our physics. And because they've done that, we have to accept that while we're holding that to account. No. But we need to isolate these claims and actually demonstrate them in order for them to hold weight, which you cannot do. So it doesn't qualify.
Exactly. No, yeah, exactly. Completely agree. I think I'm gonna go ahead and call it.
Cool.
Pretty late over here. It's 1 a.m. So Sure. Any last thoughts? Sure.
I just want to say my mannerisms in regards to these sorts of people. Look, see if somebody is really honest and they can engage in honest discourse with manners and respect, then they get the same in return. But see, and I don't mean this like he was bullying you, Will, and like you can't hold your own. I don't mean it like that. But I feel I want to step up and stand by you. Like I think we all should when we see injustice, when we see bullying, we should all show a front. And I'm going to come up and step by your side and say "fuck you" and spit in his face, because that's no a productive, progressive way to move forward. You know, if you're gonna come and spit in my face, I'm gonna spit right back in your face and fight fire with fire. Fuck you. You know, I don't accept it. So if people behave like that, you're gonna get the same in return.
Fair enough. No, yeah, again, at the end of the day, you know, the truth is not going to change. Reality is what it is. But again, the more people that represent it, the faster that this is going to move forward, you know? Yeah. So, you know, I do appreciate you, you know, coming in and, you know, sharing your thoughts and, you know, having the discussion.
Yeah. And the marker for me is look at the examples of myself and William in the street. Look at how those conversations go. That's reality. That's what it means when you engage with honest people who can discern and have manners and respect. People at PK are weak-minded, you know, infantile, hiding behind, you know, faceless accounts on YouTube, trying to intimidate and antagonize people and cause strain. It's not a discussion that's progressive, you know. So the example for me is how William behaves and how I would behave on the street. These people online are just antagonizers. They don't deserve any respect.
Yeah, I agree. Yeah, this was obviously my first open panel, you know, so just wanted to see what he had to offer, but obviously clearly off the bat, you know, he just couldn't get off his first, you know, points that were not really points, you know, with the airplane example and the train example, you know, he was just stuck on those two things and he just couldn't get past them, even though we were giving him, you know, pretty simple answers.
Yeah.
You know, but again, yes.
The guy doesn't even comprehend, you know, what the word change means. You know, change as an acceleration. If something changes, you know, that's, you know, if it's at rest and a change happens, if it's at rest and it moves, then it has to accelerate to move. I mean,
exactly. No, again, and then again, I'll go back to like the mainstream science. Again, people like to, especially Globers, right? First law of motion. Again, an object at rest will remain at rest unless acted by an external force. So again, if these people are claiming that there's a downward acceleration from an object being at rest and then released, well, then guess what? You require a force. So the fact that they admit that there is no force in free fall, but yet the first law states that you need a force to accelerate, it debunks itself, you know? So just wanted to highlight that. So yeah, I'm gonna go ahead and call it. Thanks again, Del, for coming on. Appreciate that. And everybody in chat, thanks again for, you know, for showing support. And yeah, I'll see you guys on the next one. All right, cheers. All right, take care.